Hello there, and welcome to the Cosmographer. Under a mountain in Italy, 250 kilograms of sodium iodide crystal have been recording a signal for 25 years at a statistical significance of 13.7 sigma, and no other detector on Earth has ever seen it. That is number 5 on this list. Number 12 is a moon whose two hemispheres are chemically opposite and whose near side is still 200 degrees warmer than its far side today. Number 11 is a star that lit the daytime sky for 23 days in 1054, which China, Japan, and the Arab world all recorded and which Europe did not. Number 4 is a black hole whose corona was destroyed in 40 days and then rebuilt itself in 100. Over the next 4 hours, we count down 13 unsolved problems in astronomy, ordered not by how strange they are, but by how much would have to be rewritten if any one of them were solved tomorrow. Get comfortable and settle in. If you are the sort of person who finds open questions more restful than answered ones, a quiet like and subscribe genuinely helps this channel reach more people who feel the same way. Because the item at the top of this list is not something we never knew. It is something we thought we had already settled, and it decides how the universe ends. Let's begin at number 13. Number 13, the Ashen light of Venus. There is a particular kind of list that gets made about space, and you have probably seen it. It contains the same 12 or so items every time. There is a radio signal from 1977 that somebody wrote a word on in red pen. There is a star that dimmed strangely and turned out to be dust. There is a cigar-shaped rock that passed through the solar system and was, on careful examination, a rock. These are good stories. They have also been told so many times that the telling has worn smooth, and most of them are no longer genuinely open. This is not that list. Every item on this countdown is a problem that people are arguing about right now, in journals, with their careers attached. Some of them are 4 centuries old. Some of them are 18 months old. What they share is that nobody has the answer, and the people best placed to find it will tell you so directly if you ask them. The ordering principle here is not distance, and it is not strangeness. It is consequence. Each item is placed according to how much would have to be rewritten if it were solved tomorrow. At number 13, the answer would change 1 page in a planetary science textbook. By the time we reach number 1, the answer determines how the universe ends. That is the shape of the next 4 hours, and we are going to take them slowly. We begin with something that people have been reporting since 1643, that no camera has ever caught, and that will not go away. Venus, when it is well placed in the sky, shows phases. It goes through crescents and gibbous shapes, exactly as the moon does, for exactly the same reason, and through a decent telescope, the crescent is one of the finest sights in the solar system. It is also brutally bright. Venus is the most reflective planet in the solar system, wrapped in cloud that returns about 3/4 of the sunlight falling on it, and the sunlit portion is dazzling even at low magnification. The part that should not be visible is the rest of it. The night side of Venus, the portion turned away from the sun, should be simply absent, a bite taken out of the sky. For 383 years, observers have been reporting that they can see it. They describe it as a faint grey luminosity filling the dark part of the disk, sometimes reddish, sometimes described as ash-colored. That last description gave it the name it still carries. The French called it lumière cendrée, ash-colored light, by analogy with the earthshine that lets you see the dark portion of a crescent moon on a clear evening. The name stuck, and the analogy did not, for reasons we will get to. The first detailed record belongs to Giovanni Battista Riccioli, a Jesuit astronomer working in Bologna, on the 9th of January 1643. He published it 8 years later in his enormous survey of astronomy, the Almagestum Novum. And the detail that almost every popular account leaves out is that Riccioli did not believe what he had seen. He wrote that the colors arise from the various refraction of light in the glass, as it happens with triangular glasses. He was describing what we would now call chromatic aberration, and he was explaining his own observation away. The first man to record the Ashen light also recorded that he thought it was an artifact of his telescope. There is an earlier claim. Another Jesuit, Athanasius Kircher, described something similar seen at Palermo in the spring of 1638. By the late 1700s, Friedrich von Hahn was publishing drawings in the Berlin Astronomical Yearbook with the night side of Venus carefully hatched in to show the glow. By the 19th century, it was an established phenomenon, in the sense that everyone had heard of it and nobody could account for it. The first explanation anyone reaches for is earthshine, and it fails immediately on arithmetic. Earthshine works on the moon because Earth is enormous in the lunar sky and only 380,000 kilometers away. Venus, at its closest approach, is 40 million kilometers from us. A full Earth seen from Venus would be a bright point, not a lamp, and the light it delivers to the Venusian night side is at least 11,000 times weaker than the earthshine that lights the moon. There is nothing there to reflect. Whatever the Ashen light is, it is not us. The people reporting it are not a fringe. William Herschel reported it, and Herschel discovered a planet. Patrick Moore reported it repeatedly across 6 decades of observing. Dale Cruikshank reported it. William Hartmann saw it in daylight in 1962, which is a harder observation than seeing it at night, and his sketch of that sighting became the cover image of the standard modern study of the whole question. What makes this more than a collection of anecdotes is that somebody counted. Richard McKim and Patrick Moore went through the archives of the British Astronomical Association's Mercury and Venus section, covering the observations of that section's first 2 directors from 1892 to 1999. Between them, Henry McEwen in Glasgow and Patrick Moore in southern England produced more than a century of continuous, systematic, carefully logged observations of Venus by 2 people who knew exactly what they were looking at. Of the 136 elongations of Venus in that period, 56 were adequately observed. The Ashen light was recorded at 25 of them. That is about 45%, which is far too high to be a handful of eccentrics and far too low to be something always there. The breakdown is where it becomes interesting. Of 41 evening elongations, when Venus hangs in the western sky after sunset, the light was reported at 21. That is 51%. Of 15 morning elongations, when Venus rises before the sun, it was reported at 4. That is 27%. The phenomenon appears to prefer the evening. Other datasets agree that it is common. An amateur campaign in 1988 logged 190 positive sightings across 700 night-side observations. Joseph Levine compiled 129 sightings between 1954 and 1962. There were what observers call outbreaks, periods when it was reported almost continuously for over a month, in 1953 and again in 1956, with further clusters in 1895, 1935, 1940, 1957, 1980, and 1988. And there is serious counter-evidence, which belongs here too. Daniel Barbier ran an intensive French observing campaign from the middle of August to the beginning of October 1935, watching specifically for this, and saw nothing whatsoever. Paul Abel, who currently directs the same British section that produced the best positive dataset in existence, said in 2022 that across decades of observing Venus, he has never once seen it. The single most awkward result in the McKim and Moore analysis is a negative one. Visibility of the Ashen light does not correlate with the quality of the seeing on the night in question. It does not correlate with the 8-year cycle that governs how Venus is presented to us. Both of those are exactly what you would expect an artifact of Earth's atmosphere or of observing geometry to do, and it does neither. So it should be simple. Photograph it. Nobody has. In 383 years, no visible light image from any telescope on Earth has ever shown emission from the night side of Venus. The obstacle is dynamic range. The sunlit crescent is overwhelmingly bright and needs a short exposure. The glow, if it exists, is faint and needs a long one. Estimates put the required brightness at around 1/10,000th of the sunlit disk, which is the sort of contrast that ruins photographic plates and saturates detectors. 2 experiments were designed specifically to defeat that problem, and the method was elegant. Wait for the moon to pass in front of Venus, and watch the moment when the night side of Venus emerges from behind the lunar limb while the crescent is still hidden. For a few seconds, you would be looking at the dark hemisphere alone, with the glare removed. On the 17th of July 2001, telescopes of 61 centimeters aperture watched a 67% lit Venus emerge from behind a 13% lit moon. Nothing. On the 8th of October 2015, near Alice Springs in Central Australia, David and Joan Dunham watched a 40% lit Venus emerge from the unlit limb of a 15% lit moon, using a 10-inch telescope with a video camera and a second instrument for visual work. Nothing again. For decades, the best physical explanation was lightning, and the case for it was reasonable. The Venera 9 spacecraft recorded irregular optical pulses in October 1975. Venera 11 and 12 recorded very low-frequency radio impulses. Venus Express detected Whistler mode waves in 2007, which on Earth are produced by lightning. Better still, the radio impulses peaked near 9 in the evening Venus local time, which matched the evening preference in the visual record rather nicely. The required output was calculated at around 1 trillion watts, which works out to something like 1,000 cloud flashes every second, planet-wide and permanent. Then the spacecraft evidence went the other way, and it went decisively. Cassini flew past Venus twice on its way to Saturn, in April 1998 and June 1999, carrying a radio and plasma wave instrument. It detected precisely 0 impulsive signals from Venus. The same instrument, during Cassini's Earth flyby in August 1999, detected terrestrial lightning continuously at up to 70 impulses per second. The instrument worked. Venus was quiet. Then Japan's Akatsuki orbiter arrived with a camera built specifically to catch Venusian lightning. It accumulated 16.8 hours of night-side observation through July 2019 and detected nothing at all. Earth, watched for that long by the same camera, would have produced thousands of flashes. There is genuine glow on Venus, and this is where the story becomes properly frustrating. 3 night glows are confirmed. Molecular oxygen emits at 1.27 microns from a layer around 96 kilometers up, produced when oxygen atoms broken apart by sunlight on the day side are carried around to the night side and recombine. Nitric oxide emits in the ultraviolet, peaking at about 113 kilometers. Hydroxyl emits as well. All 3 are real, all 3 are measured, and not one of them is visible to a human eye. They are infrared and ultraviolet. There is one visible candidate. Atomic oxygen produces a green line at 557.7 nanometers, the same emission that makes terrestrial aurorae green, and it was detected on Venus at about 150 Rayleighs using the Keck telescope in November 1999, near the peak of the solar cycle. It has never reached that brightness again. It was absent from the Venera missions and absent from Venus Express. And the more it has been studied, the more it looks driven by solar storms rather than by ordinary chemistry, appearing after coronal mass ejections strike the planet and fading between them. Parker Solar Probe added a final, strange detail. Its wide-field imager photographed the Venusian night side in July 2020 and again in February 2021, and made the first optical detection of the actual surface of Venus, glowing faintly through the clouds, along with a bright rim of oxygen night glow at the limb. The surface is at 464 degrees Celsius. That is just below the temperature at which a heated object begins to glow visibly to human eyes, and the fraction of that radiated energy falling in the visible band is roughly 1 part in 100 million. So the honest position is this. Something has been seen by careful observers at nearly half of all well-watched apparitions for 383 years, with a consistent preference for the evening sky and no correlation with the conditions that ought to govern an illusion. Every physical mechanism proposed for it is either invisible to the eye or too faint by orders of magnitude, or has been ruled out by a spacecraft in orbit. And no camera has ever caught it. The most likely explanation remains that the human visual system, presented with a bright crescent whose full circular outline it already knows, fills in the missing disk. That would be an ordinary finding about perception rather than about Venus. It would also have to explain why the filling in happens twice as often after sunset as before sunrise, and why it comes in decade-long outbreaks. But the next object on this list is not 40 million kilometers away, and we have walked on it. Number 12, the Moon's two faces. The Moon is the second most studied object in the sky, after the Sun. 12 people have stood on it. 6 missions have brought pieces of it home, and 3 more have done so robotically. A pair of spacecraft mapped its gravitational field to a precision that would let you weigh a mountain range from orbit. There is no body in the solar system, our own planet aside, that we have examined so thoroughly. Its 2 hemispheres do not match. Not slightly. Not in a way that averages out with better data. They differ in composition, in the thickness of the crust, in volcanic history, in water content, in magnetic history, and in the temperature of the mantle underneath them at this moment. Nobody knows why. Start with what anyone can see. The near side of the Moon carries the dark patches that generations of people have read faces and animals into. Those patches are Maria, from the Latin for seas, because early observers thought that was what they were. They are in fact enormous plains of solidified basalt, lava that welled up through the crust and flooded low-lying basins between about 3.5 and 3 billion years ago. They cover roughly 31% of the near-side surface. On the far side, Maria cover about 1%. Nobody knew this until 1959, when the Soviet probe Luna 3 returned the first photographs of the hemisphere permanently turned away from Earth. The images were grainy and low contrast, and they caused something close to disbelief among the people looking at them. The far side was not a mirror of the near side. It was a different kind of landscape entirely, pale, saturated with craters, and almost entirely without the dark plains that define the face we know. Let me put you there for a moment. Standing on the far side of the Moon, the first thing you would notice is what is missing from the sky. Earth is not there. It has never been there. This is the only surface in the inner solar system from which our planet has never once been visible, because the Moon turned this face away before there was anyone to see it and has held it there ever since. The sky is black and full of stars, and entirely without a home in it. The ground is pale grey, an anorthosite highland crust, and it is cratered on every scale you can resolve. Craters sit inside craters, going back 4 billion years without interruption, because nothing has ever flooded them and nothing has ever worn them down. To the south, the ground falls away into the South Pole Aitken Basin, 2,600 kilometers across, the largest confirmed impact structure on the Moon and one of the largest in the solar system. It should be a lava lake. It is not. And it is quiet in a way no place on Earth is quiet. The far side is the only radio-shielded surface in the Earth-Moon system, permanently screened from every transmitter our species operates, which is why radio astronomers regard it as the most valuable real estate off Earth. Now the numbers, because the numbers are where the problem lives. The Grail mission put 2 spacecraft named Ebb and Flow into lunar orbit, flying in formation from December 2011 to December 2012. By measuring the changing distance between them to a fraction of a micron, it mapped the Moon's gravity field with extraordinary precision, and from that mapped the thickness of the crust. The far side crust is on average about 20 kilometers thicker than the near side crust. Near side crust runs roughly 30 to 40 kilometers deep. Far side highland crust runs 50 to 60. Grail also revised the Moon's average crustal thickness downward to between 34 and 43 kilometers, because it found the highlands to be far less dense than anyone had assumed, with an average porosity of about 12% extending kilometers down. The Moon's outer shell is more shattered than we thought, and much more shattered on one side than the other. Composition splits the same way. The near side hosts a region geologists call the Procellarum creep terrain, and the acronym is worth unpacking because it explains a great deal. K is potassium, ReE is rare earth elements, P is phosphorus. Those elements are geochemically awkward. They do not fit comfortably into the crystal structures of the common lunar minerals, so as the Moon's original magma ocean froze, they were progressively concentrated into whatever liquid was left. Concentrated with them were uranium and thorium, which are radioactive, which means that region of the Moon has been generating its own heat for 4 billion years. The far side highlands are anorthositic, thicker, and depleted in all of it. Laboratory work at lunar mantle conditions shows that the near side's enrichment lowers the melting point enough to produce between 4 and 13 times more magma beneath the near side crust than beneath the far side. That looks like an answer, and it is not, because it does not explain itself. Why is the heat-producing material all on one side? And thin crust alone cannot be the whole story either, which the South Pole Aitken Basin proves. That impact excavated an enormous volume of crust, possibly reaching the mantle. If thin crust made Maria, its floor should be one continuous sheet of basalt. Only 3 to 4% of it carries typical lava plains. There are 4 serious models, and no consensus among the people who study this. The differential cooling model starts from the fact that the Moon formed about 15 times closer to Earth than it is now, and locked into synchronous rotation almost immediately. At that time, the proto-Earth was a glowing body at around 2,500 degrees Celsius, filling a large part of the lunar sky. The near side was being radiantly heated by it. On that model, the near side stayed molten longer, the far side crystallized first, and elements like aluminium and calcium vaporized on the hot side, drifted around, and condensed on the cold one, building the far side a thicker crust out of the near side's material. The second Moon model belongs to Martin Utzi and Eric Asfog, published in 2011. Simulations of the disk of debris that formed the Moon routinely produce more than one body. Their proposal is that a companion moon, perhaps a 30th of the Moon's mass, eventually collided with the far side at a speed low enough that it did not excavate a crater at all. It simply piled up. A slow collision does not blast material away, it accretes. The resulting layer matches the dimensions and structure of the far side highlands rather well. The third model argues the South Pole Aitken impact itself thickened the far side lithosphere and suppressed eruption there. The fourth invokes asymmetric tidal heating during the Moon's early orbital evolution. two results in the last 2 years have made all of this considerably sharper. In May 2025, Ryan Park's group at the Jet Propulsion Laboratory published a reanalysis of the GRAIL data looking at how the Moon flexes. The Moon's orbit is not circular, so the tidal force stretching it changes over the course of each month, and the body of the Moon deforms in response. How much it deforms, and in what pattern, depends on what it is made of and how hot that material is. They found that one particular component of that flexing was about 72% larger than a uniform Moon should produce. The clean explanation is that the mantle's stiffness differs by 2 to 3% between the two hemispheres, which requires a temperature difference of roughly 100 to 200 Kelvin. The near-side mantle, the same mantle that produced the Maria 3 billion years ago, is still warmer than the far side today. And in June 2024, Chang'e 6 landed inside the South Pole Aitken Basin and returned the first samples ever collected from the far side. The results have come out steadily since. The basalt dates to 2,830 million years, with an uncertainty of 5 million, which is remarkably precise for a rock that old. Its mantle source is what geochemists call ultra-depleted, and it contains essentially no creep component at all. The far-side mantle is not merely different from the near-side mantle. In its trace element chemistry, it is close to the opposite. The same mission dated the South Pole Aitken impact itself to 4.25 billion years, established that far-side volcanism ran for at least 1.4 billion years, and found significantly lower water content than near-side samples. We now have two hemispheres of the same body, formed from the same collision, that are chemically distinct, thermally distinct today, and structurally distinct, and four competing explanations, none of which has won. Two further lunar puzzles sit alongside this one and are worth having straight, because both are frequently misdescribed. The first is the ringing. On the 20th of November 1969, the Apollo 12 crew, having finished on the surface, deliberately crashed their lunar module's ascent stage back into the Moon at 1.68 kilometers per second, close to the seismometer they had just deployed. The signal that came back built slowly, peaked several minutes after the impact, and took close to an hour to fade. It was about 4 times longer than terrestrial models predicted. The following April, the Apollo 13 third stage was steered into the Moon north of Mare Cognitum, producing a signal 20 to 30 times larger that ran for over 3 hours. The Moon rang. That is a true statement, and it has been used for decades to argue that the Moon is hollow, which it is not. The explanation is well established, and it is more interesting than the myth. Beneath the fine lunar soil lie kilometers of megaregolith, rock shattered by 4 billion years of impacts into a chaotic jumble of fractured blocks. Seismic waves entering that layer scatter constantly, arriving at the detector from every direction over a long interval rather than as a single sharp pulse. And because there is no water anywhere in the lunar rock, the energy is barely damped at all. On Earth, water in pore spaces and along grain boundaries absorbs seismic energy quickly. The Moon's measured quality factor for these waves is around 3,600, far above any terrestrial crustal rock. What is genuinely open is the structure of that megaregolith, how deep it goes, how fractured it is, which is still being modeled from 4 stations of 1970s instrumentation. The second puzzle is the Moon's magnetism, and this one is currently a live fight. The Moon has no magnetic field today, but the Apollo samples came back magnetized. Benjamin Weiss and Sonia Tiku established a lunar dynamo running from at least 4.25 billion years ago to 3.56, with surface field strengths between 20 and 110 microslesla, averaging around 78 in the Mare basalts. Earth's present surface field is around 50. Later work extended a weaker field forward to somewhere between 1.9 and 0.8 billion years ago. The problem is that this should not be possible. The Moon's core is a few hundred kilometers across, 1 to 2% of its mass, and no standard dynamo scaling produces Earth-strength surface fields from a core that small, let alone sustains one for 2.5 billion years. Since 2021, John Tarduno's group has been dismantling the evidence rather than the theory. They showed that impact glass from a crater only 2 million years old carries a strong, Earth-like magnetization, which proves that impacts alone can imprint intense signals without any dynamo at all. More damagingly, they showed that certain crystals from Apollo samples aged 3.9, 3.6, 3.3, and 3.2 billion years are perfectly capable of recording a strong core field, and simply do not. Chang'e 6's far-side result, 5 to 21 microtesla at 2.8 billion years, drops a data point into a gap that was previously empty, and it does not settle the argument either. And if the Moon can keep a secret that large in plain sight, so can the historical record, which brings us to a star that lit the daytime sky for over 3 weeks, and a continent that did not write it down. Number 11. The star that lit the day. On the 4th of July, 1054, a star appeared in the constellation Taurus that was bright enough to see in broad daylight. It stayed visible in daylight for 23 days. It remained visible at night for nearly 2 years after that. Chinese astronomers recorded it in detail. A Japanese court poet recorded it. An Arabic physician recorded it, though for reasons of his own. And across the whole of literate, monastery-dense, chronicle-keeping Europe, there is not one securely dated account of it. That is the first half of the mystery. The second half is that the object it left behind is missing roughly half the mass of the star that made it. Let us take the records first, because they are better than most people expect. The Chinese account is precise enough that we can check it 970 years later. The event falls in the first year of the Zhe He era, under Emperor Renzong of the Song dynasty. The two oldest sources, the Song Hui Yao and the Song Shi, were compiled within decades of the event rather than centuries. The date is given using the 60-day cycle of day names, and it converts unambiguously to the 4th of July, 1054. The court astronomer who reported it was named Yang Weidi, and his report is a small masterpiece of political self-preservation. He describes the guest star, Kexing, the standard Chinese term for a temporary object in the sky, and then immediately frames it as an auspicious omen. The fact that the star has not overrun a particular constellation, he writes, and that its brightness must represent a person of great value. He was telling the emperor that a new star had appeared, and that it meant good things about him. Astronomy in the Song court was a department of state, and a badly interpreted omen could end a career. The physical description is what matters. It appeared at dawn, in the east, close to the star the Chinese called Tianguan, which we call Zeta Tauri, a third magnitude star at the tip of the bull's horn. It had been seen in daylight, like Venus. It had rays stemming in all directions, and its color was reddish-white. Altogether visible for 23 days. That 23 days almost certainly means 23 days of daylight visibility, because the phrase follows directly on the statement about daytime brightness. The Song Shi separately records the object's disappearance on the 6th of April, 1056, which gives 642 days of visibility in total. For nearly 2 years, there was an extra star in the sky over China, and for the first 3 weeks of that you could find it while the sun was up. There is a position problem in the record that fueled decades of doubt. The Chinese sources place the guest star to the southeast of Tianguan, several inches away. The Crab Nebula, which is what remains of it, lies to the northwest of Zeta Tauri. The distance is right, The unit translated as inch works out to roughly 1/10 to 1/5 of a degree, so several inches means about a degree, which fits perfectly. It was the direction that appeared wrong, and for a while that was used to argue that the guest star and the crab were unrelated objects. David Green and Richard Stevenson resolved it in 2003 by testing the phrasing against cases where the answer is known. They went through 18 conjunctions recorded in the Song Shi using the same standing on guard construction, involving planets whose positions can be computed exactly for any date. In 15 of the 18 cases, the object described this way was actually to the north, and it was never in the south quadrant. The phrase carries a conventional orientation, not a compass bearing. It is a formula, not a measurement. Japan records it in the Megetsuki, the diary of the poet and courtier Fujiwara no Teika, who was drawing on the records of a court astrologer. A guest star appeared in the degrees of 2 specific lunar mansions, viewed in the direction of the east, emerging from the Tianguan star, and it was as big as Jupiter. The Japanese date falls 1 lunar month earlier than the Chinese one, which is generally explained as a copying error between 2 similar characters for the 4th and 5th months. There is exactly one Arabic account, which is itself odd, because the supernova of 1006, an earlier and even brighter event, was noted by several Arab chroniclers. This one was found only in 1978, buried in a 13th century collection of physicians' biographies, quoting the Nestorian Christian physician Ibn Butlan. He writes that one of the famous epidemics of our time occurred when a spectacular star appeared in Gemini in the year 446, that in the autumn of that year 14,000 people were buried in Constantinople, and that in the middle of the following summer the majority of the people of Fustat, which is Old Cairo, and all foreigners died. The Islamic year 446 runs from April 1054 to April 1055, which fits. But notice what this document actually is. It is not an astronomical observation. It is an explanation of a plague. The star is being named as the cause. The North American petroglyph evidence, which turns up in almost every popular account, is much weaker than its reputation. In 1955, an optical engineer at Palomar named William Miller proposed that 2 rock art panels in Arizona showing a crescent beside a circle depict the conjunction of the moon and the new star on the morning of the 5th of July, 1054. The scholarly response has been severe. The supposed supernova image at White Mesa is markedly brighter and fresher than the securely dated ancestral Pueblo art at the same site, which suggests it is far later. The supernova would not have been visible from the vantage point Miller identified. The emblem more plausibly depicts a known figure from Hopi and Zuni tradition. And a crescent beside a bright point is exactly what the moon looks like next to Venus or Jupiter, which happens several times every year. The question that finishes the argument is simple. Why would these communities record 1054 and not 1006, which was substantially brighter and equally visible from the same latitude, which leaves the European silence? Europe did record the supernova of 1006. There are numerous documents. For 1054 there is nothing confirmed, and 6 candidate documents have been proposed since 1980, all 6 with problems. The most cited is a Bologna chronicle describing a very brightly shining star entering the circle of the new moon. It is a promising sentence, and everything around it is wrong. It dates the event to 1058. It gives the Emperor Henry III 49 years of reign when the correct figure is 39, and he died in 1056. The entry sits out of chronological order in a chronicle that is otherwise ordered, and it describes a lunar configuration that did not occur on the date it gives. Robert Newton found the explanation. He located 2 exactly dated entries in a different chronicle using nearly identical Latin phrasing, one for February 1086, when Venus was occulted by the Moon, and one for August 1096, when the Moon passed close to Jupiter. The Bologna entry is a routine lunar conjunction, described in standard language from a different year. The others fare no better. An Irish entry in the Annals of the Four Masters describes a round circle of fire seen at a place called Ros Ela for 5 hours during the day on the feast of St. George, with countless black birds passing in front of it and a larger bird in the center. That is a vivid image, and it is at least as likely to be a solar halo or an aurora, or something the chronicler was told about second-hand. A Flemish text from a church at Udenburg that no longer exists describes a circle of extraordinary brightness in the sky for half an hour on the 14th of April. An Umbrian account describes a pilgrim near Todi seeing something like a road strewn with shining cloths and glittering with countless lamps, on the day Pope Leo IX died. None of these describes a star, and none of them is dated to July. 4 of the 6 candidate European documents are dated to the spring of 1054, before the supernova appeared. That is the strongest single objection to the whole enterprise. Stevenson and Green's assessment in 2003 was blunt. This is confirmation bias, scholars anxious to ensure that the event was recorded by Europeans. So why the silence? There are 4 plausible reasons, and no proof of any of them. The first is doctrinal. European natural philosophy at the time was Aristotelian, and Aristotle held that everything above the sphere of the Moon was perfect and unchanging. Change belonged to the corruptible world below. A new star was therefore not merely surprising, it was theologically inadmissible, the kind of observation a chronicler might reasonably decline to record rather than be obliged to explain. The second is survival. Medieval chronicles are patchy things, and a great many have been lost. The third is technical. Europe had lost the observational vocabulary of classical antiquity. The candidate European texts contain no astronomical terminology whatsoever, while the Chinese sources fix the position to within a degree of a named star. Even if a European monk saw it, he may not have had the language to record it usefully. And the fourth is timing, and it is either coincidence or it is not. The star reached its maximum daylight brightness at almost exactly the moment of the East-West Schism. Patriarch Michael Cerularius was excommunicated on the 16th of July, 1054, 12 days after the star appeared. Whatever else was occupying the Latin Church that month, a new object in the sky being read as an omen was not something it had any incentive to publicize. Now the object itself, which has its own problem. The Crab Nebula sits about 6,500 light-years away, which means the star actually exploded around 5,500 years before anyone in China looked up. It has been expanding for 970 years and is now roughly 11 light-years across. At its center is the Crab Pulsar, a neutron star spinning 30 times a second, whose wind powers the entire structure. Add up what is there. The visible ejecta amount to about 4.6 solar masses. The pulsar accounts for another 1.4. The star that exploded should have been somewhere between 8 and 13 solar masses. Between 4 and 6 solar masses are unaccounted for. The energy is worse. The nebula's kinetic energy comes out at about 7 times 10 to the 49th ergs. A normal core collapse supernova releases around 10 to the 51st. The Crab is more than a factor of 10 too feeble. Robert Chevalier proposed in 1977 that there must be a fast outer shell, moving ahead of the visible nebula, carrying the missing mass and the missing energy with it. That is a reasonable prediction, and it has been tested for nearly 50 years, in optical light, in radio, and in X-rays. No convincing shell has been found. Chandra observations concluded that on standard blast wave analysis, it is not there. The elegant alternative is that the Crab was never a normal supernova. Kenichi Nomoto and colleagues proposed from around 1981 that it was an electron capture supernova. In a star of 8 to 10 solar masses, the core ends up made of oxygen, neon, and magnesium rather than iron. Electrons get captured onto those nuclei, the pressure supporting the core drops away, and the collapse produces a weak shock that ejects only the star's loose outer envelope. Both the low energy and the observed chemistry follow naturally. The Crab became the template for an entire subenergetic class. Then, in June 2024, the James Webb Space Telescope measured the nickel and iron emission lines in the Crab with its mid-infrared instrument. Electron capture predicts a nickel-to-iron ratio far above the solar value. UIST found the ratio elevated, but only modestly, and much lower than previous estimates had suggested. The result remains consistent with electron capture. It no longer excludes an ordinary low-mass iron core collapse. After 40 years, the mechanism that produced the best documented supernova in human history is less settled than it was. Just over a century later, 5 men in Kent saw something on the edge of the moon and swore an oath about it. And for 50 years, one reading of that oath was that they had watched a crater being born. Number 10. The Flaming Torch, on the Horn of the Moon. It is about an hour after sunset on the 18th of June, 1178. You are in Canterbury, in Kent, and there are 4 other men with you. There is no artificial light of any consequence. The cathedral is behind you, and the town is going quiet in the way towns did when the working day ended with the daylight. The western sky still holds some color. Low in it, thin as a paring, is the new crescent moon. You are looking at it because it is worth looking at, and because there is nothing else to do. The upper horn of the crescent splits in 2. From the midpoint of the split, something rises. It is described afterwards as a flaming torch, throwing out fire and hot coals and sparks. The body of the moon below it writhes, and the word used is that it throbbed like a wounded snake. Then it settles. Then it happens again. It happens a dozen times or more. The flame takes twisting shapes each time, and each time the moon returns to normal. 5 men watch this, in a century in which every educated person in Europe has been taught that the heavens above the sphere of the moon do not change, cannot change, and are not the kind of thing that changes. Afterwards, they swear to it. The chronicler Gervase of Canterbury records that the witnesses were prepared to stake their honor on an oath that they had made no addition and no falsification to what they had seen. That account sits today in the library of Trinity College, Cambridge. The Latin was printed in 1879. And for roughly 50 years after 1976, there was a serious scientific proposal that these 5 men were the only human beings who have ever watched a crater form on the moon. The proposal came from Jack Hartung in a paper published in the journal Meteoritics, with the title asking, plainly, whether the formation of a 20-kilometer impact crater on the moon had been observed on that date. His candidate was a crater called Giordano Bruno. It is 22 kilometers across, sitting at 36 degrees north and 103 degrees east, which is to say, just around the edge of the far side, on the northeastern limb. That is exactly where the upper horn of a young crescent moon points from the northern hemisphere. The crater fits the description of something new in every visual respect. It has an exceptionally bright ray system, with streaks of fresh ejecta running more than 100 kilometers out across the surrounding surface. Rays darken over time as the solar wind and micrometeorites weather them, so bright rays mean young. It has no central peak. Its walls are sharp. Hartung called it the youngest lunar crater of its size or larger anywhere on the moon. For reasonable impact speeds, the object that made it would have been between 1 and 3 kilometers across. Paul Withers later noted, in passing, that the same object arriving at Earth instead would have been a civilization-ending event. 2 years after Hartung's paper, the hypothesis appeared to receive independent physical confirmation, and this is the part that made it stick. Apollo left retroreflectors on the lunar surface, arrays of corner cube mirrors that return a laser pulse exactly the way it came. Bouncing a laser off them from Earth measures the Earth-Moon distance to within centimeters, and doing it repeatedly over years reveals how the Moon is moving in detail. In 1978, Odile Calamet and Daryl Mulholland published an analysis in Science, which put it on the cover, interpreting the data as showing free librations, small unforced wobbles in the Moon's rotation, with an amplitude consistent with an impact roughly 800 years earlier. The Moon appeared to still be ringing from the blow the monks had seen. It has not survived, and the way it came apart is worth walking through, because it is a good demonstration of how a beautiful idea gets tested to destruction. The first objection is the missing sky. Paul Withers, then at the Lunar and Planetary Laboratory in Arizona, published the decisive analysis in 2001. Earlier work had calculated that an impact of that size would throw about 10 million tons of debris off the Moon fast enough to escape it, and that Earth would sweep up that material over the following week. Withers worked out what that would look like from the ground. For centimeter-sized fragments, you get something like 1 trillion meteors, at around magnitude 1.7, comparable to the brighter stars. For an observer looking anywhere near overhead, that is about 50,000 meteors per hour. For a week. The Great Leonid Storm of 1966, which people still talk about, reached that kind of rate for 20 minutes. An ordinary dark sky gives you a few meteors per hour. Withers wrote that a meteor storm this impressive, lasting a week, would have been considered apocalyptic by all medieval observers. There is no record of it. Not in Europe, not in the Arab world, not in China, not in Korea, not in Japan. In the same century in which Chinese astronomers were logging guest stars to within a degree, the entire planet apparently failed to notice a week in which the sky was on fire. The single candidate that has ever been offered is a Korean report, some months later, that countless stars flew west, which is far too vague and far too late. The second objection is that the laser evidence reversed. Charles Yoder analyzed a more complete dataset in 1981 and concluded that the free librations could not be explained by Hartung's impact at all. He proposed turbulent friction at the boundary between the Moon's core and mantle instead, a mechanism entirely internal to the Moon. The third objection is that the crater is far older than 800 years, and the evidence here is layered. Withers' own crater counts gave an age below 350 million years. Clementine imagery showed measurable space weathering on the ejecta. Optical maturity work brought it under 100 million. And in 2009, Tomokatsu Morota's group used the terrain camera on Japan's Kaguya spacecraft to count craters smaller than 200 meters across on Giordano Bruno's continuous ejecta blanket, a technique that works well precisely because small craters accumulate quickly. The answer came out at 1 to 10 million years, with a best fit near 4 million. Statistically, the Moon should receive an impact of that scale roughly every 15 million years anyway. 4 million years is unremarkable. 800 is not. And there is a fourth objection that troubles every interpretation, including the skeptical one. On the 18th of June, 1178, the Moon was about 1.3 days past new, and it would not have been visible from Canterbury at all. It would have been visible the following evening. Gervais gets the date of the September 1178 solar eclipse right, so this is not a chronicler who was careless with dates. The explanation that has held is the one Harvey Nunninger and Glenn Huss proposed in 1977, less than a year after Hartung's paper. The monks saw a meteor burning up in Earth's own atmosphere, at a distance of perhaps 100 kilometers, which happened by line of sight to be positioned directly in front of the Moon. Withers endorsed it and added the detail that makes it convincing. For a meteor to appear exactly superimposed on the lunar disk, an observer must be standing inside a footprint on Earth's surface only 1 or 2 kilometers across. Step outside that circle, and the meteor is simply somewhere else in the sky. Which explains exactly why 5 men sitting together in one place in Kent saw something extraordinary, and a chronicler in London, who recorded the eclipse 3 months later without difficulty, recorded nothing at all. It is worth sitting with what that means about the 5 witnesses, because the modern reconstruction is not unkind to them. They were not lying, and they were not mistaken about what they saw. They saw a bright object in a specific place, doing specific things, and they described it accurately enough that 9 centuries later we can still reason about it. They were wrong about only one thing, and it was the one thing they had no possible means of judging, how far away it was. They did the only thing available to them, which was to write it down carefully and swear to its accuracy, and that was enough to keep the question alive for 848 years, and not enough to answer it. The Canterbury event is the most famous entry in a much longer catalogue. Lunar transient phenomena. Brief glows, brightenings, obscurations, patches of color on the lunar surface have been reported for 4 centuries by people looking through good telescopes and keeping careful notes. The standard reference is NASA Technical Report R277, published in July 1968, compiled by Barbara Middlehurst with Patrick Moore and 2 colleagues. It covers 1540 to 1967 and catalogues 579 reported events from more than 300 observers. The single most controversial entry is from the 2nd of November 1958. Nikolai Kozyrev at the Crimean Astrophysical Observatory obtained a spectrogram of the central peak of the crater Alphonsus, showing bright emission bands he attributed to molecular carbon. While exposing his second plate, he noted a marked increase in the brightness of the central region and an unusual white color, after which it faded and the spectrum returned to normal. 3 colleagues examined the plates the following day. The interpretation damaged his reputation for years. It has never been reproduced, and it has never been satisfactorily explained away either. The genuinely interesting thing about the catalogue is that the reports are not evenly distributed. Arlen Krotz at Columbia tested this in 2009, splitting the data every way he could think of to see whether the pattern simply reflected which features observers happened to point at. It held up. About half of all reports cluster near the crater Aristarchus. About 16% are at Plato. About 6% fall on the youngest large impact craters. There is a further cluster at Grimaldi. Krotz concluded the clustering is imposed by the lunar surface, not by human habit. On the 19th of July 1969, Mission Control relayed to the Apollo 11 crew, then in lunar orbit, a report of activity at Aristarchus from observers on the ground. The crew looked and reported an area considerably more illuminated than the surrounding surface, which seemed to have a slight amount of fluorescence to it. There is a physical mechanism with real evidence behind it. Radon-222 is a gas with a half-life of 3.8 days, produced by the decay of uranium in rock. The alpha particle spectrometers on Apollo 15 and 16 detected enhancements of it over the Aristarchus Plateau and over Mare Fecunditatis. Lunar Prospector independently detected radon over Aristarchus and Kepler in the late 1990s and mapped polonium-210 with its 138-day half-life to identify vents that had been active over the previous 50 years or so. Something is venting gas from beneath the lunar surface, in the same places where people have been reporting glows for 400 years. Because radon decays in days, you can only detect a release if you happen to be looking within days of it. That is why outgassing remains the leading candidate and remains unproven. The modern verdict splits cleanly in two. Short flashes are real and routine. The Neliota project, using a 1.2-meter telescope at Cryonery Observatory in Greece, with twin cameras in two-color bands, had validated 193 impact flashes as of September 2025, with about 90 more too faint to confirm in both bands. Those are meteoroids hitting the moon, and the two-color requirement lets the team measure the temperature of each impact directly. The long-duration events are a different matter. Glows, obscurations, colored patches lasting minutes to more than an hour cannot be impacts. In 4 centuries, not one of them has ever been captured simultaneously by 2 independent instruments. Those 5 men left a written record we can still read and still not settle. The next 2 items on this list are records too, one in bronze, one in clay, and neither of them can be read at all. Number 9. The bronze sky and the clay Venus. 2 objects, made about 1,000 years apart, sit at the center of arguments that have run for decades and show no sign of ending. One is a disk of bronze and gold, dug out of a German hilltop by criminals. The other is a clay tablet from the library of an Assyrian king, recording 21 years of the planet Venus, which after a century and a half, nobody can date. Both of them are astronomical records. Neither of them can be read with confidence. And the people arguing about them are not fringe figures. They are the professional archaeologists and Assyriologists whose job this is. The Nebra sky disk came out of the ground in the summer of 1999, illegally. 2 men with a metal detector, Henry Westphal and Mario Renner, were working the Mittelberg, a hill near the town of Nebra in Saxony-Anhalt. What they found was a hoard: the disc, 2 bronze swords, 2 axe heads, 2 spiral arm rings and a chisel. They sold it, and it circulated on the black market for roughly 2.5 years, passing through several hands. In February 2002, the state archaeologist Harald Meller recovered it in a police sting operation in Basel, after a couple attempted to sell it to him for 700,000 Deutschmarks. It went on to the UNESCO Memory of the World Register in 2013 and now sits in the State Museum of Prehistory in Halle. The object itself is about 32 centimeters across, roughly the size of a dinner plate, made of bronze with gold leaf inlaid into its surface. The alloy is unusual, about 96.5% copper with only 2.5% tin, which is a very low tin bronze. Where those metals came from is one of the more remarkable results in European archaeology. Trace elements and lead isotope ratios trace the copper to the Mitterberg mining district in the Eastern Alps, near Salzburg, which was worked from the 18th century before the Common Era until the 9th. The gold matches natural gold from the River Carnon in Cornwall, where extraction is independently verified for the 17th and 16th centuries before the Common Era. A community in central Germany, 3,500 years ago, was assembling a single object from materials drawn from opposite ends of the continent. A study published in 2024 using electron microscopy, hardness testing, and experimental replication by working blacksmiths established that the disc was not simply cast and finished. It was made from a flat cast, followed by roughly 10 cycles of hot forging, heat to around 700 degrees Celsius, hammer, anneal, repeat. That is a considerable amount of skilled labor invested in a thin plate of metal. The museum reconstructs 5 phases in the object's life, and the sequence matters. In the first phase, there were 32 gold stars, including one tight cluster of 7, plus a gold orb and a crescent. In the second, 2 gold arcs were added along the rims, covering 2 of the existing stars, with a third star carefully relocated so that it remained visible. In the third, a shape usually described as a sun ship was added at the bottom. In the fourth, 38 holes were punched around the edge, probably so it could be mounted on a pole or a standard. And in the fifth phase, one of the two arcs was deliberately removed, in antiquity, before the object was buried. Somebody made this thing, then modified it twice, then took part of it off again, then put it in the ground. Nobody knows why any of those decisions were made. The astronomical reading is what made it famous. The tight cluster of 7 dots is standardly read as the Pleiades, which is the most recognizable star cluster in the northern sky and the one most cultures have found a use for. The two arcs each span about 82 degrees, and that number is the interesting one. It matches the angle along the horizon between the summer solstice sunrise and the winter solstice sunrise, at the latitude of the hill where it was buried. The measurement is latitude diagnostic. The disk encodes, in metal, where it was made. Wolfhard Schlosser and Ralph Hansen took it further and proposed that the disk encodes a calendar rule. A calendar based on lunar months drifts against the solar year by about 11 days annually, which means that if you want your festivals to stay in the right season, you must periodically insert a 13th month. The question every lunisolar calendar has to answer is, when? Their reading is that the disk gives the answer. When you see the Pleiades beside a crescent moon of the thickness shown on the disk, a young crescent, but noticeably thicker than the thin sliver you would ordinarily expect at that point in the year, the calendar has drifted far enough that a leap month must be added. Hansen connected the rule to a comparable Babylonian intercalation rule, preserved in a cuneiform text. If that reading is right, the disk is not a picture of the sky. It is an instrument for keeping time, encoding a rule that would otherwise have to be memorized and transmitted orally. In 2020, Rupert Gebhardt and Rüdiger Krause published a paper arguing that the entire framework is wrong. Their case had 3 parts. The hoard is not a closed find. The objects were not necessarily deposited together. The disk may not even come from the Mittelberg at all. And as a context-free single object, datable only by style, it belongs to the Iron Age, somewhere between 850 years before the Common Era, a full millennium later than the standard date. They pointed out that no comparable motifs appear on early Bronze Age artifacts. If they were right, every astronomical interpretation would collapse because the disk would post-date the material it is supposed to be evidence about. A 13-author team led by Ernst Pernicka replied the same year, and the reply is unusually direct for an academic exchange. The find spot, they argue, is verified several ways over, by the looter's sworn court testimony, by follow-up excavation at the site, by terrain markings, by pickaxe traces, by a water bottle the looters discarded, and by elevated gold and copper concentrations in the sediment from prolonged burial of metal. Soil samples from the find spot match sediment still adhering to the disk, to one of the swords, and to an axe. The copper in the disk and in the accompanying finds comes from the same Salzburg region deposit, whose production ends in the 9th century before the Common Era, a century before the Iron Age date even begins. Tin and lead isotope ratios correlate with numerous early Bronze Age objects. The boat motif is typical of the Bronze Age and unknown in the Iron Age. And radiocarbon dates on organic remains preserved inside one of the swords come out at around 1600 before the Common Era. They accuse the challengers of arguing with incomplete and in places incorrect data, and of selectively citing early material while ignoring 20 years of subsequent results. The overwhelming weight of institutional opinion is now early Bronze Age, somewhere around 1800 to 1600 years before the Common Era. But the exchange was never resolved by any formal procedure. It simply stopped, with both papers in print. And what remains genuinely unsettled either way is whether the astronomical readings, particularly the leap month rule, are what the makers intended, or whether they are a modern pattern imposed on an object whose actual purpose was something else entirely. The second object is clay. It is known as the Venus tablet of Amisaduqa, and formerly as Tablet 63 of a long Babylonian omen series. The best-known copy is Neo-Assyrian, 7th century before the Common Era, 17 centimeters by 9, excavated at the Mound of Nineveh in what is now northern Iraq. Austin Henry Layard dug there from 1848 and found the first great cache of tablets in late 1849. Hormuzd Rassam found the library of Ashurbanipal a few years later. Over 30,000 tablets and fragments from those excavations are in the British Museum today. The same excavations produced the Epic of Gilgamesh. Henry Rawlinson and George Smith published this one in 1870 under the title Tablet of Movements of the Planet Venus and Their Influences. What it records is a specific, repeatable astronomical measurement. Venus, being closer to the Sun than we are, periodically disappears into the Sun's glare and reappears on the other side. The dates on which it first becomes visible and last remains visible are sharp events, easy to observe and dependent on the geometry of the orbits. The tablet records those first and last visibilities expressed in lunar dates over a run of 21 consecutive years with an omen attached to each. The observations were made during the reign of Amisaduqa, the fourth king after Hammurabi in the first dynasty of Babylon. Around 20 copies are known, mostly fragmentary, falling into 6 groups. The oldest was found at Kish in 1924. In 1912, Franz Xaver Kugler noticed that a year name mentioned in the text, the year of the Golden Throne, corresponds to Amisaduqa's 8th regnal year. That converted an omen text into something else entirely, a potential absolute date anchor for the whole chronology of the ancient Near East. If you can match those 21 years of Venus observations to the real sky, you know exactly when Hammurabi's dynasty ruled, and everything else in Mesopotamian history hangs off that. And that is where it stopped working, for a reason that is elegantly annoying. Venus's cycle of appearances very nearly repeats every 8 years. 5 of its synodic periods fit almost exactly into 8 of our years, with only a small residual drift. That means a 21-year pattern of Venus events can be matched to the real sky at several widely separated epochs, and the fits are close enough that the observations themselves cannot distinguish between them. The offsets between the candidate solutions are 56 years and 64 years, which is why there is not a date, but a family of chronologies. The high chronology puts the observations at about 1702 before the Common Era. The middle chronology at 1646 or 1638. The low at 1582. The ultra-low at 1550. Mainstream scholarship recognizes 5 positions spread across roughly 2 centuries. The tablet has its own internal problems layered on top. The surviving copies are first millennium reproductions of a mid-second millennium original, 1,000 years of hand copying by scribes who were not astronomers. The entries for at least 2 of the 21 years describe things Venus physically cannot do and are treated as corruptions. Retrocalculating when a planet first becomes visible depends on atmospheric refraction and on extinction near the horizon, both of which are model-dependent, and on the uncertain rate at which Earth's rotation has been slowing over 3,500 years. And in 2000, Vahe Gurzadyan argued that the 56 and 64-year cycle cannot actually be traced in the tablet at all, which removes the very assumption the entire chronological framework had been resting on. There is now an external constraint, and it is genuine progress. Sturt Manning's team at Cornell published a study in 2016 matching radiocarbon measurements against tree ring sequences from juniper timbers in a palace at Aksimhoyuk in Turkey. Timbers found in association with clay ceilings bearing the seal impressions of a known king, and from a second site. The result is compatible only with the middle chronology, excluding the others. That is a real answer. But notice its shape. It is an outside measurement telling us which of the tablet's possible readings to select. The tablet, after 156 years of work, still does not decide for itself. Those observers were watching a sun that had been getting brighter for 4.5 billion years, and the early history of that brightening is a problem nobody has solved. Number 8. The sun that was too dim for the world. It warmed. On the 7th of July 1972, Carl Sagan and George Mullen published a short paper in the journal Science that created a problem nobody has cleanly solved in the 54 years since. It is not speculation. It is arithmetic, and the arithmetic says that the early Earth should have been frozen solid, and it very obviously was not. The stellar physics is not in dispute by anyone. A star on the main sequence gets brighter as it ages, and the reason is straightforward once you see it. Hydrogen fusion takes 4 protons and makes 1 helium nucleus. That reduces the number of particles in the core. Fewer particles at the same temperature means less pressure, so the core contracts slightly under its own gravity, which heats it, which raises the fusion rate, which raises the luminosity. The sun has been slowly turning up its own output for 4.5 billion years, and it will keep doing so. Run that backwards. At 4 billion years ago, the sun was radiating about 70% of what it radiates now. Across the whole of the Archean eon, from 3.8 to 2.5 billion years ago, it was running 20 to 25% below present output. Take that dimmer sun and put it above an Earth with today's atmosphere and today's reflectivity, and the mean surface temperature comes out below the freezing point of water until roughly 2 billion years ago. A completely frozen planet for more than half of its existence. Sagan and Mullen pointed out that a luminosity change of only about 2% is enough to matter for habitability. This is 15 times that. The geology says, flatly, that it did not happen. The evidence starts almost impossibly early. The Jack Hills in Western Australia contain zircon crystals eroded out of rocks that no longer exist, the oldest dated at 4,404 million years, within about 150 million years of the planet forming. Those zircons carry oxygen isotope values slightly elevated above the mantle value, and the interpretation is specific. Their parent rock sat at the surface and interacted with liquid water at low temperature before being buried and remelted. Liquid water, that early. In southwest Greenland, the Isua supracrustal belt contains pillow basalts from 3.8 to 3.7 billion years ago. Pillow basalt forms only when lava erupts underwater. The outer skin chills instantly, and the flow advances as a series of bulbous lobes. The thickest unit there is a kilometer deep, which requires eruption under at least a kilometer of standing water. In the Pilbara Craton of Western Australia, there are stromatolites, layered structures built by microbial mats trapping sediment, in rocks 3.48 billion years old, with more across the Warrawoona group, alongside 3.5 billion year old hot spring deposits. That is not merely liquid water. That is a functioning biosphere in warm, shallow seas, under a sun a quarter fainter than the one outside your window. 4 serious solutions have been proposed. Each has a specific problem that has not gone away. The obvious one is a much stronger greenhouse from carbon dioxide, regulated by the silicate weathering thermostat. That thermostat is real, and it is elegant. Warmer and wetter conditions accelerate the chemical weathering of rock, which pulls carbon dioxide out of the atmosphere, which cools the planet, which slows the weathering. It is a genuine negative feedback, operating over millions of years, and it is the reason Earth's climate has been broadly stable across geological time. The obstacle is a mineral. Rob Rye, Philip Kuo, and Heinrich Holland examined ancient soils, paleosols, formed between 2.75 and 2.2 billion years ago. In those soils, iron was reprecipitated as iron silicate minerals rather than as siderite, which is iron carbonate. Siderite forms when there is plenty of carbon dioxide around. Its absence, therefore, sets a ceiling, below about 0.04 of a bar, roughly 100 times the pre-industrial level. Climate models need at least 5 times more carbon dioxide than that ceiling allows. Later work has contested the siderite argument, so the constraint is real, but not final. The second solution is methane. Molecule for molecule, it is a far more powerful greenhouse gas, and in an oxygen-free Archean atmosphere, produced by methane-generating microbes, it could have accumulated to levels impossible today. Methane defeats itself. Its photochemistry generates a hydrocarbon haze, the same orange smog that shrouds Titan, and that haze absorbs and scatters incoming sunlight high in the atmosphere. It warms the stratosphere and cools the ground beneath it. Modeling by Sean Domagal-Goldman, James Casting, and Jacob Hack-Misra found that a thin haze begins to form once methane reaches about 1/10 of the carbon dioxide abundance, at which point you have gained only about 5 Kelvin of warming. Push past that ratio, and adding more methane makes the surface colder, not warmer. There is a ceiling built into the mechanism. The third solution is a darker planet. Minnick Rosing, Dennis Bird, Norman Sleep, and Christian Bjerrum argued in 2010 that the early Earth simply reflected less sunlight back to space. There was far less continental crust, so less bright land and more dark ocean. And, crucially, there were no biologically produced cloud condensation nuclei, because the marine organisms that manufacture them had not evolved. Fewer nuclei mean clouds made of fewer, larger droplets, and such clouds reflect noticeably less. Colin Goldblatt and Kevin Zarnler replied the following year with a paper whose title states the conclusion: "The faint young sun paradox remains." Under the most generous assumptions available, reducing cloud and surface reflectivity falls short by a factor of 2. You cannot darken the planet enough. The fourth solution is a thicker atmosphere. Nitrogen is not a greenhouse gas. It does not absorb infrared radiation. But more of it broadens the absorption lines of the gases that do, through simple collisional physics, which makes a given amount of carbon dioxide or water vapor more effective. Goldblatt's group calculated roughly 2 to 5 Kelvin of warming per doubling of nitrogen. The geology runs the wrong way. Fossil raindrop imprints, the pits left where rain fell on volcanic ash 2.7 billion years ago, whose size depends on how much air resistance the drops encountered, limit the air density then to less than twice modern. A 2016 study of gases trapped in ancient rock constrained the pressure at the same epoch to less than half of modern. The early atmosphere appears to have been thinner, not thicker. There was a fifth idea, and it is effectively dead. If the young sun had been more massive, it would have been brighter, and it could have shed the difference since. Keeping Earth above freezing that way requires enormous mass loss sustained for 2 to 3 billion years. Observations of young stars like the Sun show they lose most of their mass in the first 100 million years, at cumulative rates far below what is needed. A review published in 2020 argues the Earth case is essentially solved, most likely by higher carbon dioxide, with secondary contributions from everything else. Not everyone agrees that the constraints permit that cleanly. What is not disputed is that the answer, if we have it, is a stack of partial contributions rather than a single mechanism, and that the magnitude of each contribution is individually argued about. And then there is Mars, where the same problem is worse and where nobody claims it is solved. Mars orbits at about 1.5 times Earth's distance from the Sun, so it receives roughly 43% of the sunlight we do. Apply the faint young sun on top of that, and early Mars was receiving something like a third of the light that falls on Earth today. Robin Wordsworth and colleagues estimate that producing even marginally warm and wet conditions there requires a greenhouse effect of around 65 Kelvin. Earth's entire present greenhouse effect, which is the difference between the planet we have and a frozen one, is about 33. Mars needs double that, and about 9 times what Mars actually has. The water evidence is not ambiguous, and it has only got stronger. Valley networks cut across the southern highlands, dendritic branching systems that look like drainage basins, because that is what they are, dated between 3.8 and 3.5 billion years ago. The erosion rates appear to have been highest precisely when the sun was faintest. Curiosity, on the floor of Gale Crater, found fine-grained mudstones at a location called Yellowknife Bay, and then an extended lake sequence in the lower slopes of Mount Sharp. The interpretation is a lake around 3.7 billion years ago, in a closed basin, plausibly lasting millions of years. Perseverance, at Jezero Crater, imaged and sampled a delta, the fan of sediment a river builds where it enters standing water, along with flood deposits. Jezero was an open lake, with an inlet and an outlet, fed by a river, quiet for most of its history and then subject to episodic flooding late in the sequence. Models cannot produce the climate that made any of that. A thick carbon dioxide atmosphere does not simply solve it, for 2 reasons that both bite. Carbon dioxide condenses at low temperature, forming clouds and effectively capping how much greenhouse warming you can get from it. And a thick carbon dioxide atmosphere scatters incoming sunlight back to space, raising the planet's reflectivity and partly cancelling the warming you were trying to achieve. Modelers have been unable to warm early Mars once condensation is properly included. The natural steady state of early Mars, in every model, is cold. The geology demands episodes of warmth. The leading fixes each fail at a specific point. Adding hydrogen to a thick carbon dioxide atmosphere produces strong collision-induced absorption, pairs of colliding molecules briefly acting as absorbers that neither molecule is on its own. Ramon Ramirez and colleagues got a surface at the freezing point from a 3-bar atmosphere of 95% carbon dioxide and 5% hydrogen, and comfortably above it at 10 to 20% hydrogen. The problem is sustaining that much hydrogen. Photochemical modeling finds the required mixing ratios very hard to maintain, because hydrogen is light and escapes. Transient warming from large impacts works locally. A big enough impact vaporizes water and injects a temporary steam atmosphere, and it rains. But the volume of water needed to carve the valley networks exceeds what impacts can deliver by at least 3 orders of magnitude. The cold and icy model proposes a globally frozen Mars, where snow accumulates preferentially on the highlands and melts episodically, driven by changes in the planet's axial tilt, by volcanism, or by impacts. It reproduces the distribution of valley networks reasonably well. It struggles badly with Gale Crater's long-lived lake. In April 2025, Curiosity found something that had been missing for 20 years. Across an 89-meter thickness of rock in the sulfate-bearing units of Mount Sharp at 3 separate drill sites, its mineralogy instrument identified siderite, that same iron carbonate, at between 4.8 and 10.5% by weight, sitting alongside highly water-soluble salts. This solved a long-standing problem. If Mars once had a thick carbon dioxide atmosphere, that carbon had to go somewhere, and the obvious destination is carbonate rock. Orbital spectroscopy had never found enough of it. The answer appears to be that siderite's spectral signature is masked in sulfate-rich contexts, so it was there and invisible. Extrapolating the measurement globally gives a sequestered carbon inventory equivalent to somewhere between 2.6 and 36 millibars of atmospheric carbon dioxide. That is a real, quantified sink, and it is a small fraction of the multi-bar atmosphere the warm models require. Coexisting iron oxyhydroxides indicate the carbon cycle was only partially closed, with some of the buried carbon returned to the air. So the position on Mars in 2026 is that we have direct physical evidence of standing water, rivers, deltas, and long-lived lakes, and no climate model that produces the conditions to make them. That is what we cannot reconstruct about the Sun's past. What is harder to accept is what we cannot model about the Sun right now. Number 7. The star we cannot simulate. The Sun is 8 light-minutes away. It is the best observed object in the universe by an enormous margin. A fleet of spacecraft watches it continuously. Neutrino detectors buried under mountains sample particles from its core. Helioseismology, the technique of reading a star's interior from the way its surface rings, gives us the temperature, density, composition, and rotation rate at every depth inside it. Until about 2005, all of that fitted together. The standard solar model matched the helioseismic measurements to better than 0.5%, everywhere, at every depth. It was held up, correctly, as one of the great successes of 20th century physics, a case where human beings had genuinely worked out the inside of a star. Then somebody remeasured what the Sun is made of, and it fell apart. 21 years later, it has not been repaired. The break came from spectroscopy, and it came from doing the job better. Martin Asplund, Nicolas Graves, and Jacques Sauval redid the analysis of the solar photosphere, the visible surface, where the absorption lines that tell you the composition are formed. Instead of the one-dimensional model atmospheres used since the 1960s, they used three-dimensional radiation hydrodynamics, which actually simulates the churning convective granulation of the surface rather than approximating it as a flat layer. They also handled the line formation without assuming local thermodynamic equilibrium, which is another approximation the older work had leaned on. By every technical criterion, the new analysis was better physics. It also lowered the abundances of carbon, nitrogen, oxygen, and neon by roughly 30 to 40%, and with them, the Sun's bulk metallicity, the ratio of everything heavier than helium to hydrogen, from about 0.023 down to roughly 0.018. Metallicity matters enormously inside a star, for a reason that is not obvious. Heavy elements are only a fraction of a percent of the mass, but they are the main source of opacity in the radiative interior. Photons trying to escape the core scatter and get absorbed by them. Change the opacity, and you change how quickly energy flows outward, which changes the temperature gradient, which changes where convection has to take over. So one change to a composition table broke 3 things simultaneously, each of which had previously matched beautifully. The first is the depth of the convection zone. Helioseismology measures the boundary between the radiative interior and the convective envelope at 0.713 solar radii, with an uncertainty of about 1 part in 1,000. That is a directly measured quantity, not an inferred one. The low metallicity models place it at 0.724. That is a 5 sigma discrepancy in something we can see. The second is the helium at the surface. Helioseismology gives a surface helium fraction of 0.2485. The models with the new abundances give 0.232. The third is the sound speed profile through the whole interior, and the disagreement is worst in a particular place, just below the base of the convection zone, at the tachocline. That is the thin shear layer where the differentially rotating convective envelope meets the solid body rotation of the radiative interior, and it is where the solar dynamo, the machine that generates the Sun's magnetic field and drives the sunspot cycle, is thought to live. Of all the places for the model to disagree with the star, that is the least convenient. Asplan's group revisited the entire problem in 2021, reassessing all 83 long-lived elements. The metallicity came back very slightly up, to 0.0187, mainly from a revised neon abundance, measured in actual solar wind particles, returned to Earth by the Genesis mission. Their own stated conclusion was that the solar modeling problem remains intact, suggesting shortcomings in the computed opacities or in the treatment of mixing below the convection zone. Opacity is the leading suspect, and there is a remarkable experiment behind that suspicion. In 2015, Jim Bailey and Taisuke Nagayama's team at Sandia National Laboratories used the Z machine, the most powerful laboratory X-ray source on Earth, to measure the opacity of iron at electron temperatures between 1.9 and 2.3 million Kelvin, at densities matching the base of the solar convection zone. They did not calculate the opacity. They created the conditions and measured what happened. The result came out between 30 and 400% higher than theory predicted, depending on wavelength. Substituting the measured iron opacity into solar models raised the overall mean opacity by about 7%, which is roughly half of what is needed to close the gap. Nobody has explained theoretically where the extra opacity comes from. The atomic physics of iron in that state is supposed to be understood. The experiment has been contested on the grounds of how well the plasma conditions were diagnosed, which is a fair objection to any measurement that hard. It has not been overturned. Every other proposed fix is either a free parameter or unconfirmed. Enhanced mixing below the convection zone can be tuned until the models agree, but tuning is not prediction. Accretion of metal-poor material onto the young sun requires a fine-tuned accretion history that nothing else supports. Energy transport by dark matter particles in the core has been explored seriously and reduces but does not eliminate the discrepancy, and is now squeezed hard by the null results of direct detection experiments. Raising the metallicity using solar wind measurements was attempted and directly refuted. And then the neutrinos made it stranger. Neutrinos are produced in the core and leave essentially unimpeded, arriving 8 minutes later. They are the only direct probe of the sun's center we possess. Everything else is inference. In November 2020, the Borexino detector at Gran Sasso announced the first detection of neutrinos from the carbon-nitrogen-oxygen cycle, the sun's secondary fusion channel, at 5.1 sigma. That cycle uses carbon, nitrogen, and oxygen as catalysts, so its rate depends directly on how much of those elements the core actually contains. Borexino's final result agrees with the high metallicity models. It sits in about 2 sigma tension with the low metallicity ones, and combined with the beryllium and boron neutrino fluxes, it disfavors the low metallicity model at 3.1 sigma. So the sun's surface spectrum says one thing about its composition, and its core neutrinos say something else, and there is no accepted way to make both true. There is something worth pausing on in that story, because it is not a story about failure. For decades, the agreement between the standard solar model and helioseismology was one of the results physicists were proudest of. Then a group of careful people did a better measurement, using better physics, and broke it. Nobody made a mistake. The improvement was real, and the breakage was real, and the same people who broke it are, 21 years later, the ones working hardest to repair it. That is what the process looks like from inside when it is working properly, and it is not comfortable. That is the first of 3 problems with our own star. The second is rotation. In 2017, Eric Fossart, Patrick Boumier and colleagues analyzed 16.5 years of data from the Golf instrument aboard the SOHO spacecraft. They were hunting for gravity modes, oscillations that penetrate the deep core, where the ordinary acoustic modes barely reach. Gravity modes have been sought for 6 decades and have never been unambiguously detected, because by the time they reach the surface, they are extraordinarily weak. Rather than detect them directly, the team looked for their imprint on the round-trip travel time of the ordinary pressure modes. And they reported that the solar core rotates 3.8 times faster than the radiative envelope above it, a rotation period of about 1 week at the center, against roughly 27 days at the surface. If true, that is a significant result about how the Sun formed and how it has shed angular momentum. It is also fragile in a specific and troubling way. Hannah Schunker and colleagues showed the following year that the detection vanishes if the start time of the 16.5-year time series is shifted by as little as 2 hours, or if the data are sampled at 60 seconds instead of 80. Their published assessment was that the result is extremely fragile and should be treated with utmost caution. No independent group has reproduced it. The question of how fast the middle of our star is turning is, in 2026, open. The third problem is the one with practical consequences for satellites, power grids, and anyone flying at altitude. Nobody can predict the solar cycle. The roughly 11-year sunspot cycle, 22 years if you count magnetic polarity, which physically you should, has resisted first principles amplitude prediction for 2 centuries. It is not for lack of effort, and the failures are on the record. The expert panel convened in 2007 to forecast cycle 24 could not reach agreement and issued 2 predictions, a peak sunspot number of 140 in October 2011 or a peak of 90 in August 2012. The observed peak was around 113 to 116. More tellingly, the mean of all published cycle 24 forecasts was 165 with a spread of 43, and the actual value fell outside that range entirely. For cycle 25, the official panel in December 2019 predicted a peak of 115 in July 2025. By October 2023, the Space Weather Prediction Center had revised that to a range of 137 to 173, peaking sometime in 2024. The actual smoothed sunspot number peaked at 160.8 in October 2024, well above the original consensus, and about 15 months earlier than forecast. One group did considerably better with a completely different approach. Scott McIntosh and colleagues identified what they call termination events, the abrupt disappearance of a magnetic band at the solar equator, sometimes completed within a single 27-day rotation. Cataloging 14 of these across more than a century of records, they found that the interval between terminators correlates with the amplitude of the next cycle. They identified the cycle 24 terminator in mid-2020 and forecast cycle 25 at 190 plus or minus 20. That is an overshoot, but it is far closer to 161 than 115 was. And underneath the prediction problem sits a more fundamental one, which is that the cycle can simply stop. Between 1645 and 1715, during the period John Eddy named the Maunder minimum, fewer than 50 sunspots were recorded across a 28-year window, in which today we would expect 40 to 50,000. That is not a small dip. That is the machine going quiet. A reassessment in 2015 across multiple independent datasets confirmed it was a genuine grand minimum and not an artifact of who happened to be observing. A shallower version, the Dalton minimum, followed around 1790 to 1830. There is no model that tells us when the next one begins. It is worth stopping for a moment because we have come a long way down this list and the ground has shifted more than it might feel like. We started with a glow on Venus that 4 centuries of observers have reported and no camera has recorded. We went to a moon whose 2 hemispheres are chemically opposite and whose near side is still warmer today. We went to a supernova that lit the daytime sky and left no European record, and to a nebula missing half its mass. We went to 5 men in Kent and a catalogue of lights on the lunar surface that nobody has ever caught twice. We went to a bronze disk and a clay tablet that we can hold and cannot read. We went to a sun too faint for the planet it warmed. And now we are at a star 8 light minutes away, whose composition, core rotation, and next decade of behavior are all, in 2026, unsettled. Everything so far has been within reach: the solar system, our own history, our own star. Everything from here is not. If the star 8 light minutes away is this hard to model, it is worth asking what the first few 100 million years of the universe look like when you finally build a telescope that can see them. Number 6. The galaxies that assembled too quickly. When the James Webb Space Telescope opened its eye in the summer of 2022, everybody knew roughly what it was going to find, because the models were mature and the predictions were specific. The first few 100 million years after the Big Bang were supposed to be a slow, faint beginning. Small clumps of gas collapsing inside small dark matter halos. Stars made almost entirely of hydrogen and helium because nothing had yet lived and died to make anything else. Galaxies that were dim, tiny, chemically primitive, and rare. What the telescope found was a universe that had already got on with things. 4 years later, the gap between the prediction and the observation has narrowed in places, widened in others, and has not closed. Start with where the frontier actually is, because it is worth being precise. The current record holders sit at redshift 14. JADE's GSZ140 was announced in May 2024 with a spectroscopic redshift of 14.32, which places it about 290 million years after the Big Bang. ALMA, the radio array in the Chilean desert, later detected its doubly ionized oxygen line at 88 microns and tightened that redshift by a factor of more than 180. In May 2025, Rohan Naidu's team announced a galaxy at redshift 14.44, roughly 280 million years after the beginning. That is still the record. As of now, there is no spectroscopically confirmed galaxy above redshift 15. Redshift 14 means the light has been stretched by a factor of 15 on its way here. Ultraviolet light, emitted by hot young stars, arrives as mid-infrared. That is precisely why this population was invisible to Hubble and why a telescope had to be built for the infrared, cooled to about 40 Kelvin, and flown 1.5 million kilometers from Earth where it could stay cold. The problem is not that these galaxies exist. It is what they contain. JADE's GSZ140 is spatially resolved. You can see that it has an extent, with a half-light radius of 260 parsecs. That matters, because it means the light is starlight, spread across a region, not a single accreting point source. Its stellar mass is around 500 million suns. Its ultraviolet brightness puts it among the most luminous objects known at any redshift above 8. It is forming stars at about 25 solar masses per year, and its oxygen abundance is roughly 1/10 to 1/5 of the sun's. That is the number that stops people. Oxygen does not exist until massive stars manufacture it in their cores and then die and scatter it. 290 million years after the beginning of everything, this object already contains about 10 times more heavy elements than the models expected. On the evidence of its low gas fraction, it has also already converted or expelled most of its fuel. It is not a young galaxy in any useful sense. It is a galaxy that has already lived through a great deal. There is a related absence worth naming here, because it is a hole in the record rather than a contradiction in it. The universe's first generation of stars, made of nothing but hydrogen and helium, with no heavy elements at all, because none existed yet, has never been observed. Not once, at any redshift, by any instrument. Theory says those stars should have been enormous, hot, short-lived and blue. Every galaxy we have ever looked at, including the ones at redshift 14, already contains heavy elements, which means we are always looking at the second generation or later. The first stars either formed earlier than we can currently reach, or died faster than we assumed, or were fewer than the models require. Nobody knows which. Now for the part that requires honesty, because the most famous version of this story has partly unraveled, and it is more useful to say so. In 2023, Evo Lab's team reported 6 massive candidate galaxies from the first observations of one UST survey at redshifts around 7 to 9, 5 to 700 million years after the Big Bang. One of them appeared to reach 100 billion solar masses. At that epoch, a galaxy that massive would contain more ordinary matter than its entire dark matter halo could plausibly have gathered. The story went around the world as the impossible early galaxies, and there were serious headlines about whether cosmology was broken. Spectroscopic follow-up has substantially deflated it. The spectral feature that Lab's team interpreted as a Balmer break, the signature of a large population of evolved stars, turns out in most cases to be the signature of an accreting black hole instead. A dedicated spectroscopic census found that essentially all the point-like sources with that characteristic red and blue spectral shape show broad emission lines when you look properly, which is the fingerprint of gas orbiting close to a black hole. Model the red light as a reddened accretion disk rather than as billions of old stars, and the inferred stellar masses fall sharply. That particular crisis is largely resolved, and it should be reported as resolved. Genuinely ultra-massive early systems do remain, a population of dust-obscured objects documented in 2024 converts ordinary matter into stars at efficiencies that are difficult to produce in any model. But the headline about a broken cosmology was an overreach, and one of the things that separates a real open problem from a story is whether people are willing to say when they got one wrong. What has not resolved is the little red dots. Jorrit Matthie's group identified them as a distinct population in 2024. They are extremely compact, essentially point-like, and they have a characteristic spectral shape that observers describe as V-shaped, blue in the rest frame ultraviolet, then turning sharply red in the rest frame optical. Their number density is intermediate in an interesting way, about 100 times rarer than ordinary star-forming galaxies, but far more abundant than bright quasars. They cluster in a window between redshift 4 and 8, which is roughly 1 billion years wide. And below redshift 3, their number density collapses. Whatever they appear, they are common for a while, and then they stop. Nobody has explained the disappearance either. The scandal was the mass ratio. In the nearby universe, a supermassive black hole is typically between 1/10 and 0.5% of its host galaxy's stellar mass. That relationship holds across a huge range of galaxy sizes, and it is one of the load-bearing results in extragalactic astronomy. It is why people believe black holes and galaxies grow together, regulating each other. In the little red dots, the inferred black holes came out at 10 to 30% of the host's stellar mass. In the most extreme cases, the black hole appeared to outweigh every star in the galaxy combined. They are also anomalously faint in X-rays and in radio, which is exactly wrong for a normally accreting quasar. Accretion at that rate should be blazing in X-rays. In March 2025, 2 complementary papers proposed a way out, and it is a genuinely strange idea. They call it a black hole star. The proposal is that a little red dot is a black hole wrapped in a dense ionized gas cocoon that behaves in some respects like a stellar atmosphere. If that is right, then the broadening of the emission lines, which is how black hole masses are estimated, does not come from gas orbiting at high speed. It comes from electron scattering inside the cocoon, which smears the lines in a way that mimics fast motion. Correct for that, and the black hole masses drop by roughly 2 orders of magnitude, to somewhere between 100,000 and 10 million solar masses. The same picture explains the missing X-rays and radio because the cocoon absorbs them. It explains the apparent Balmer break as absorption in dense gas rather than old stars. And it explains the red continuum as reprocessed emission from the gas itself. In 2026, a stacking analysis by Madison Brooks and collaborators pushed in the same direction from a different angle. They combined the spectra of around 2,000 early galaxies from 4 duest surveys, grouped by brightness and redshift. The logic is that individual detections preferentially catch the most extreme objects. You only see a black hole individually if it is unusually bright for its host, so the published sample is biased toward the upper envelope. Stacking removes that bias. The stacked result places early black holes considerably closer to the local relation. That is progress, and it is not a resolution. The competing explanations are all still live. Primordial black holes formed in the first instance of the universe, direct collapse black holes forming from gas clouds that never fragmented into stars, and hosts that are unusually gas-rich and dark matter-dominated. And the underlying difficulty has not gone anywhere because it is a timing problem rather than a mass problem. Quasars powered by black holes of 1 billion solar masses have been found less than 700 million years after the Big Bang. Growing a black hole takes time, and there is a physical speed limit on it. Radiation pressure from the infalling material pushes outward on the material still falling in, which caps the accretion rate. Start from the collapse of an ordinary massive star, a seed of perhaps 100 solar masses, feed it at the theoretical maximum continuously without pause, and you still struggle to reach 1 billion solar masses in the time available. Something either made much larger seeds or found a way to exceed the limit, and both options require physics we have not observed. In March 2026, Yost added a further complication by finding overmassive black holes in dwarf galaxies, which are the last places anybody expected them. Then there is a galaxy with a catalog name that nobody will remember, ZF-UDS 7329, which poses a different kind of problem and a sharper one. It contains about 100 billion solar masses of stars. It is spectroscopically confirmed at redshift 3.205. And it is quiescent. Star formation has stopped entirely. Carl Glazebrook's team showed in 2024 that it formed the bulk of those stars in a fast burst, lasting 200 to 400 million years, roughly 1.5 billion years before the moment we observe it, which places the formation inside the universe's first 1.5 billion years. The difficulty is not the stars. Stars can form quickly if the gas is there. The difficulty is the scaffolding. In the standard picture, galaxies assemble inside dark matter halos that themselves grow by merging, and that growth follows a well-defined statistical history. At that epoch, halos massive enough to gather and hold 100 billion solar masses of stars are not predicted to exist in useful numbers. A follow-up study classes the object a relic galaxy. It has barely changed since. Age-dating systematics and measurements of how color varies across the galaxy can ease the tension. They have not erased it. It is worth being clear about why the halo is the hard part, because it is easy to hear this as a quibble about bookkeeping. In the standard picture, ordinary matter cannot collapse into a galaxy on its own. It needs a gravitational well already dug for it by dark matter, and those wells grow by merging with each other, which takes time. The rate at which they merge is not a free parameter. It follows from the initial spectrum of density fluctuations, which is measured independently from the microwave background. So when a galaxy turns up with more stars than the available wells can account for at that moment in cosmic history, the problem is not the galaxy. The problem is that two independent measurements, one of the early universe's lumpiness, one of a specific object's mass, are being asked to fit together and are not fitting. And this is not one object. A survey of ultra-massive quiescent galaxies across a range of early redshifts finds the same pattern repeated: too much stellar mass, formed too fast, shut down too early. The population version of the problem is harder to explain away than any individual case, because a single galaxy can be a statistical fluke and a population cannot. The last piece of this item is reionization, and it is a good illustration of how a crisis can arrive and then mostly leave. The early universe went through phases. For the first few 100,000 years, it was an ionized plasma, opaque to light. Then it cooled enough for electrons and protons to combine into neutral hydrogen. The light broke free, and the universe went dark. Then, something ionized the hydrogen again, and by around redshift 5 or 6 that process was complete. Which is why the universe is transparent today. In February 2024, Hakeem Atek's team used the gravitational lens of the galaxy cluster Abell 2744, a natural telescope that magnifies whatever lies behind it, to obtain the first spectra of very low-mass galaxies less than 1 billion years after the Big Bang. They concluded that faint dwarf galaxies are abundant enough and produce enough ionizing radiation to have done the job. Then the arithmetic overshot. Julian Munoz and colleagues published a paper later that year asking whether there was now a photon budget crisis. Just had found both a high efficiency of ionizing photon production per unit of starlight and more galaxies at high redshift than expected. Combine those with escape fractions extrapolated from nearby galaxies, how much of the ionizing radiation actually gets out of a galaxy rather than being absorbed inside it, and the galaxies already observed would not merely have reionized the universe. They would have finished the job far too early, contradicting the timeline we measure from quasar spectra and from the microwave background. That crisis is now largely resolved, and it resolved in a way that undercuts the original headline. Direct measurements of escape fractions in galaxies actually inside the reionization era find no relationship between escape fraction and brightness, which invalidates the extrapolation from nearby analogues and give average values low enough for a late finish. But the question of who did it is wide open. A paper published this month argues the opposite of Atek, that a small minority of bright sources, rather than the faint majority, dominates the ionizing budget. 2 years after the question was declared answered, nobody agrees on which galaxies lit the universe. Every one of those problems assumes we know what dark matter is. Under a mountain in Italy, one apparatus has been claiming to have found it, alone, for 1/4 of a century. Number 5. The detector that has been alone for 25 years. There is a motorway tunnel that runs for 10 kilometers through the Gran Sasso Massif in the Italian Apennines. About halfway along it, a side passage leads off to a set of halls carved into the rock, and inside those halls are some of the most sensitive instruments ever built. 1,400 meters of limestone sit overhead. That is about 3.5 kilometers of water equivalent, and it reduces the cosmic ray muon flux by roughly a factor of 1,000,000. The point of putting a laboratory under a mountain is not secrecy, it is silence. In one of those halls sits an array of thallium-doped sodium iodide crystals, about 250 kilograms of them, wrapped in copper and surrounded by shielding, watched continuously by photomultiplier tubes waiting for flashes of light corresponding to a few thousand electron volts of deposited energy. Consider what that apparatus is actually doing. The room is not still. The mountain is not still. The whole assembly is being carried around the Sun at 30 kilometers per second, and the Sun is being carried around the center of the galaxy at 230. If the Milky Way is embedded in a halo of dark matter particles, which is what the rotation of every galaxy we have ever measured implies, then that apparatus is moving through a wind of them, permanently, and slightly faster in June than in December. It is built to feel that difference. It has been recording an annual variation in its event rate for more than 2 decades. The variation has the period, the phase, the amplitude, the energy range, and the event topology that a galactic dark matter wind is predicted to produce. The statistical significance is 13.7 sigma. No other detector on Earth has ever seen it. It is worth restating briefly why anyone is looking. Galaxies rotate too fast for the matter we can see. Measure how quickly stars orbit the center of a spiral galaxy, add up the mass of everything luminous, and the stars in the outskirts should have been flung off long ago. The same discrepancy appears in the motions of galaxies within clusters, in the way clusters bend the light of objects behind them, and in the pattern of temperature fluctuations in the cosmic microwave background, 3 completely independent kinds of measurement at completely different scales, all requiring about 5 times more matter than we can account for with atoms. Something is there. In 40 years of looking, nobody has caught a single particle of it in a laboratory and been believed. There is also a point about the technology that makes Dharma's persistence more awkward rather than less. Thallium-doped sodium iodide is not an exotic apparatus. It is a 1940s detector material, cheap, operating at room temperature, thoroughly characterized, used routinely in medical imaging and radiation monitoring. This is not a case of one group with a uniquely delicate instrument nobody else can replicate. It is a case of one group with a very ordinary instrument, run for a very long time, with extraordinary care taken over radioactive purity. The physical idea goes back to André Drucker, Catherine Fries, and David Spergel in 1986, and it is a beautiful piece of reasoning, because it turns a null detection problem into a timing problem. The trouble with looking for dark matter is that you cannot switch it off. There is no way to run a control experiment with the dark matter removed, so any excess of events you see could always be some background you have not understood. The annual modulation idea sidesteps that entirely. Earth's orbit is inclined about 60 degrees to the Sun's motion through the galaxy. In June, our orbital velocity partly adds to the Sun's, and we move through the halo faster. In December, it partly subtracts. Faster motion means the particles arrive with more energy, which means more of them cross a detector's minimum threshold. So the rate should vary sinusoidally, with a period of exactly 1 year, peaking around the 2nd of June and reaching a minimum around the 2nd of December, with an amplitude of only a few %. It should appear only in a narrow, low-energy window. And, this is the elegant part, it should appear only in single-hit events. A dark matter particle interacts so weakly that scattering twice in the same apparatus is effectively impossible, whereas a stray neutron or gamma ray frequently deposits energy in 2 crystals at once. You can therefore use your own detector's multiple hit events as a real-time background monitor. Dharma has all of it. Led by Rita Bernabé of the University of Rome Tor Vergata, running since 1995 and in its current configuration since 2003, the experiment reports the following. Over 22 annual cycles and 2.86 ton-years of exposure, in the energy window from 2 to 6 kilo-electron-volts, a modulation at 13.7 sigma. The measured amplitude is about 1/100th of a count per day per kilogram per kilo-electron-volt. The measured phase is 145 days, which is the 25th of May, consistent with the predicted date within about 1.5 sigma. The measured period is 0.999 years, plus or minus 1,000th. The phase is the strongest single piece of evidence in its favor, and it deserves emphasis. A random instrumental systematic has no particular reason to peak within a week of a date derived from the Sun's velocity around the galactic center. And every other dark matter experiment says no. For a standard weakly interacting massive particle, The region of parameter space Dharma occupies has been excluded by Xenont, by Lux Zeppelin, by Panda X, by Super CDMS, by Pico, and by DarkSide. A global analysis published in 2025 describes the exclusion as reaching a full 6 orders of magnitude below Dharma's region of interest. That is not a marginal disagreement. That is a factor of 1,000,000. Lux Zeppelin released 417 live days of data in December 2025, the largest dark matter dataset ever collected by any experiment, with no signal, while incidentally detecting neutrinos from the Sun, which tells you how sensitive it is. For 2 decades, Dharma had a defense, and it was not an unreasonable one. Nobody else was using sodium iodide. Different target nuclei have different sensitivities, and some models could in principle produce a signal in sodium and iodine while staying invisible to xenon and germanium. If you want to test Dharma properly, you have to build Dharma. 3 groups did exactly that. Anais 112 runs 112 kilograms of sodium iodide in the Canfranc underground laboratory in the Spanish Pyrenees, and it has been operating since August 2017 under a blind protocol fixed before data taking began. That last detail matters more than it sounds. The analysis was written down, in full, before anybody was allowed to look at the data, which means the result could not be tuned toward an expected answer, even unconsciously. Its 6-year result, published in 2025 with an effective exposure of 626 kilogram years, is incompatible with Dharma at 4 sigma in the lower energy window and 3.5 sigma in the higher one. Cosine 100 ran 106 kilograms of the same material in the Yangyang underground laboratory in South Korea, immersed in a liquid scintillator VITO from September 2016 to March 2023. Its full dataset finds no annual modulation and challenges Dharma at over 3 sigma. Cosine also ran the single most awkward test in this whole story. The collaboration took Dharma's own background subtraction procedure and applied it to Cosine's data. It produced a clear annual modulation of similar amplitude, with the opposite phase. A method that manufactures a signal out of a dataset containing none is not a method anybody wants underneath their headline result. Combined, Anais and Cosine exclude the Dharma signal at 4.68 sigma in the 1 to 6 kilo electron volt window. A global fit published in October 2025 asked the sharpest possible version of the question. Forget models for a moment. Is there any recoil spectrum whatsoever, of any shape, which, after being filtered through each detector's own light yield, resolution and binning, could produce Dharma's signal while remaining invisible to the other 2? The answer was that Dharma sits in 5.1 sigma tension with the combination. Letting Dharma keep its own assumed calibration constants only reduces that to 4.63. And with fully generic parameterizations, the tension stays above 5 sigma unless you fine-tune into configurations that are frankly absurd, requiring sodium recoils to peak in summer while iodine recoils peak in winter in the same crystal. A 4th experiment is about to add something none of the others can, and the idea behind it is very simple. Sabre South sits 1,025 meters underground at the Starwell Underground Physics Laboratory in Victoria, Australia, the first deep underground laboratory in the Southern Hemisphere, built in a former gold mine. Assembly finished through 2025, with commissioning this year and science data expected by the end of it. The point is the latitude. Every seasonal effect on Earth, muon flux, neutron flux, radon concentration, temperature, humidity, groundwater, inverts between the hemispheres. A genuine galactic dark matter modulation does not, because it depends on Earth's orbital velocity, which does not care which hemisphere your detector is in. If Dharma's signal is terrestrial, Sabre South will see it 6 months out of phase. If it is galactic, Sabre South will see it in phase. That is about as clean a discriminator as experimental physics ever gets. Meanwhile, the mundane explanations have been examined, and mostly they fail. The cosmic muon rate at Gran Sasso does modulate annually, peaking in summer as the upper atmosphere expands and shifts where cosmic ray secondaries are produced. But its phase lags Dharma's by about 30 days, and its amplitude is far too small. A more sophisticated proposal in 2014 noted that adding a component of neutrons induced by solar boron neutrinos shifts the combined phase forward to match Dharma's. Dharma's rebuttal calculates that even assuming a 10% modulation in the neutron flux with exactly the right phase, the induced amplitude sits 2 to 3 orders of magnitude below what is observed. The most serious criticism is different in kind, and it is about arithmetic rather than physics. In 2020, Dario Buttazzo, Paolo Panci, Nicola Rossi, and Alessandro Strumia pointed out that Dharma computes its residuals by subtracting approximately yearly averages, starting from a fixed date, rather than by fitting a continuous background model. If the underlying rate is slowly drifting, and detector backgrounds generally do drift, as contaminants decay and equipment ages, that procedure generates an artificial sawtooth pattern, and a sawtooth fits a sinusoid rather well. In the extreme case, they argued, Dharma's amplitude and phase could be reinterpreted as a decade-long trend. Anais raised the same objection independently. It was rebutted the same year by a Bayesian analysis finding odds against a drifting background of more than 100 million to 1. There is one more technical detail that deserves to be better known. Converting a flash of light into a nuclear recoil energy requires a number called the quenching factor, how much light a recoiling sodium or iodine nucleus produces compared with an electron depositing the same energy. Dharma assumes constant values, 0.3 for sodium, 0.09 for iodine, and has never measured how those values change with energy in its own crystals. Every other group that has measured it finds strong energy dependence, with sodium never above about 0.2 and falling as low as 0.1 at the energies that matter most. So where does this stand in 2026? Dharma is not formally refuted. No single same-target experiment has yet published a standalone 5 sigma exclusion, though Anais ran through the end of 2025 specifically to reach that threshold. Dharma has never retracted anything, and has never identified a fault in its own apparatus. But the dark matter interpretation is, on any physically motivated model, excluded above 5 sigma by the combination of the replication experiments. And what has never been achieved, in 25 years, is an explanation of what the modulation actually is. The signal is real as a data set. Something in that mountain is varying with a 1-year period, in single-hit events only, in a narrow energy window, peaking in late May. Nobody has been able to say what. And there is a possibility underneath all of this that is rarely stated plainly. Every one of those null results, the xenon detectors, the germanium detectors, the bubble chambers, excludes dark matter having a particular mass and a particular interaction strength. They are exclusions of a hypothesis, not searches of a space. If dark matter is not a weakly interacting massive particle at all, if it is an axion, or a much lighter particle, or something that interacts in a way nobody has thought to look for, then every one of those beautifully executed experiments is consistent with dark matter existing and simply being something else. The field has spent 4 decades and a great deal of money ruling out the version of the answer that seemed most likely in 1985. That is a signal we cannot account for in a laboratory we built ourselves. 270 million light-years away, there is one we watched happen. Number 4. The black hole that lost its corona. 270 million light-years away, in the constellation Draco, there is a galaxy with a catalog designation and no name. Its central black hole weighs about 1.4 million suns, which makes it modest as supermassive black holes go, a third of the mass of the one at the center of our own galaxy. In 2018, that black hole's corona was destroyed. Not hidden, not obscured by a passing cloud of gas. Destroyed. The X-ray output of the object fell by a factor of about 10,000 in roughly 40 days. Then, over about 100 days, it rebuilt itself and came back brighter than it had been before. Since then, it has grown a jet, started oscillating, and, as of this year, stopped oscillating faster and settled into a steady rhythm. Every one of those events has happened on a timescale a person can follow. Black hole processes are usually geological. This one runs on a schedule, and for 8 years it has been the single most instructive object of its kind in the sky. Some background on what a corona is, because the disappearance only means something if you know what disappeared. Gas spiraling into a black hole forms an accretion disk, and friction heats that disk until it glows. For a black hole this size, mostly in the ultraviolet. Above and around the inner disk sits a much hotter, much thinner region of plasma at something like 1 billion Kelvin, called the corona by analogy with the sun's. When ultraviolet photons from the disk pass through it, they collide with the extremely energetic electrons there and get kicked up to X-ray energies. That process, and essentially only that process, produces the hard X-rays that are the signature of an accreting black hole. Nobody has ever imaged a corona. Its geometry is inferred from timing and spectra, and it remains one of the significant open questions in accretion physics. Which is exactly why an opportunity to watch one vanish and reassemble is worth this much attention. Before any of it happened, this galaxy was odd in a small way. It was classified as a naked Type II active galaxy, meaning it persistently lacked the broad emission lines that indicate fast-moving gas close to the center. Normally, that absence is explained by a torus of dust and gas hiding the inner region from view. This one had almost no obscuring material. Something was missing, and nothing was hiding it. That classification question is not a small one, and it is worth a moment because it explains why this object was being watched so closely afterwards. Active galaxies come in 2 broad types. Type 1 shows broad emission lines, produced by gas moving at thousands of kilometers per second, very close to the black hole. Type 2 shows only narrow lines from gas much further out. The standard explanation, held for decades, is that they are the same objects seen from different angles. If a donut of dust and gas surrounds the center and you happen to be looking edge-on through it, the fast-moving inner gas is hidden and you see a Type 2. That model has held up well in general. It fails for objects like this one, where the fast inner gas appears absent and there is nothing to hide it. Then the all-sky automated survey for supernovae, a network of small telescopes that photographs the entire visible sky every night looking for things that change, flagged an optical brightening on the 3rd of March 2018. Archival data pushed the true onset back to around the 23rd of December 2017. The visible brightness rose by more than 2 magnitudes. Within weeks, the broad hydrogen lines appeared for the first time. Broad Lyman Alpha followed in August. This made the object the first active galaxy in which the transition from Type 2 to Type 1 was resolved in time. Astronomers had argued for decades about whether those categories represent genuinely different objects or the same kind of object viewed from different angles. Here was one changing category while people watched. Then Claudio Ricci and colleagues, using the NICER instrument bolted to the outside of the International Space Station, along with SWIFT, XMM Newton, and NuSTAR, found what happened next. 3 or 4 months after the optical flare, the X-rays began to fade. By August 2018, the hard X-ray power law component was gone entirely. What remained was dominated by a black body at around 1,000,000 Kelvin, which is the disk, not the corona. There was no absorption signature, nothing was in the way. The corona was simply not there anymore. And then, about 100 days later, it returned, at something like 10 to 20 times its pre-event brightness. There are two explanations for that, and no verdict between them. Ritchie's group proposed a tidal disruption event. A star wandered close enough to the black hole that the difference in gravitational pull between its near and far sides exceeded its own self-gravity, and it was pulled apart. Roughly half the debris escapes. The rest falls back over months to years, and that stream of returning material disrupted the inner accretion flow badly enough to destroy the magnetic structure supporting the corona. Nicholas Skeppy, Mitchell Bagelman, and Jason Dexter proposed something stranger. In their model, the black hole sat in what is called a magnetically arrested disk, with strong magnetic flux of a single polarity threading the inner region and helping power the X-ray emission. A patch of magnetic flux of the opposite polarity then drifted inward with the accreting gas. As it arrived, it first brightened the ultraviolet and optical, and then cancelled the existing flux. The way two magnets brought together the wrong way round cancel each other, and the X-ray emission died with it. The observed interval of about 200 days from onset to X-ray minimum matches the cancellation timescale for a disk of the relevant size rather well. A star being eaten, or the magnetic field of an accretion disk changing sign. 8 years on, neither has been established. Both explanations are testable in principle, and neither has been cleanly tested, which is worth understanding. Tidal disruption events are now found at a rate of several per year by wide-field optical surveys, and their light curves follow a reasonably characteristic shape as the debris falls back. This object's optical behavior is not a clean match to that template. Magnetic flux inversion, meanwhile, is a process that has been simulated but never observed in any system, so there is no template to compare against at all. The instrument that caught the whole thing nicer is a soft X-ray timing telescope mounted on the outside of the International Space Station, designed originally to study the interiors of neutron stars. It happened to be in orbit, capable of pointing at a target repeatedly over months, at exactly the moment this began. In February 2023, the object started doing something else. Its radio emission began climbing exponentially, ultimately reaching about 60 times its previous level, and stayed up for over a year. Eileen Meyer, Sibassish Laha and colleagues found a radio spectrum characteristic of what are called gigahertz-peaked sources, which are normally interpreted as jets younger than 1,000 years or so. Then very long baseline array observations, linking radio dishes across a continent to synthesize a telescope the size of the array, resolved bipolar extensions on either side of the core, separated by about 1/10 of a parsec. A jet was forming, in real time, in an object that had never had one. Roughly 1 in 10 active galaxies launches a powerful radio jet, and 9 in 10 do not, and nobody knows what makes the difference, which is precisely why watching one switch on matters. And then it began to keep time. Megan Masterson and colleagues, using XMM Newton monitoring from July 2022 through October 2024, found a strong millihertz oscillation in the X-ray output. In 2022, the period was about 18 minutes. 2 years later, it was 7.1 minutes. The oscillation was speeding up, and, unusually, the rate of speeding up was itself slowing down, a behavior never seen before in any black hole oscillation, stellar mass, or supermassive. A 7-minute period is the part that matters, and it is worth being concrete about what it implies. Around a black hole of 1.4 million solar masses, an orbit with a 7-minute period sits inside about 10 gravitational radii of the event horizon. Picture it. The disk is a flat sheet of gas at ultraviolet temperatures, and above it, a corona that was destroyed 6 years ago and has since rebuilt itself, now contracted down to a few gravitational radii. Below both of them is a hole in space-time with the mass of a small star cluster. And something small and dense is going around it once every 7 minutes, on an orbit roughly 20 million kilometers across, smaller than Mercury's, closed in less time than it takes to boil a kettle. At that distance, the geometry itself is distorted. Light leaving the far side of the orbit is bent around the black hole toward us. Time runs measurably slower down there than it does out here. And this light has been traveling for 270 million years. It left before the first dinosaurs, and for all but the last 8 of those years, there was nothing at this end pointed at it. The hypothesis, offered carefully by the authors themselves, is that something is orbiting. A body of about 1/10 of a solar mass, plausibly a white dwarf, the exposed core of a dead star, dense enough to hold together against tidal forces, could survive inside 10 gravitational radii of a black hole this small, and would fill its Roche lobe at roughly a 10-minute orbital period. If that is what this is, it is an extreme mass ratio in spiral, a small dense object spiraling in toward a supermassive black hole, radiating gravitational waves as it goes, at frequencies that the LISA observatory is being built to detect in the 2030s. Those systems are among the highest value targets in gravitational wave astronomy, because a small body completing thousands of orbits effectively maps the space-time around the larger one. The authors are explicit about the difficulty. Orbital decay models struggle to explain the observed period evolution without stable mass transfer offsetting the angular momentum losses. And the alternative, some kind of disk or corona instability, has no analog among stellar mass black holes, where such things would be easier to study. There is also a timing coincidence in all this that nobody has managed to explain away. The oscillation began at essentially the same moment the jet did. 2 things switched on together, in an object that had already lost and rebuilt its corona 5 years earlier. Either the jet's formation created the conditions for the oscillation, or the oscillation's cause, whatever is down there, triggered the jet, or a third process did both. There is no accepted answer, and the question is not academic. If a small orbiting body can help launch a relativistic jet, that would say something significant about the 90% of active galaxies that never launch one. The story has kept going. A separate paper in December 2025 reported even slower oscillations, at microhertz frequencies, during the period when the inner disk and corona were reforming, a second clock, running on a different timescale in the same object. Phase-resolved analysis published in late 2025 found a U-shaped relationship between the oscillation's lag and photon energy, the first ever measured for a supermassive black hole, and argued for resonant oscillations in a plasma corona that is contracting and confined to a few gravitational radii, which is a different explanation from an orbiting body. And a paper published in April 2026 reported that monitoring through January of this year shows the oscillation persisting, but plateaued at a constant 2.5 millihertz. Over 900 cycles have now been counted, more than for any other oscillation of this kind in any active galaxy on record. It has stopped speeding up. An inspiraling body should not do that. Nobody predicted the plateau, and nobody has yet explained it. There is one further complication that should be stated, because it constrains everything above. The mass of this black hole is known to roughly a factor of 2 either way. That uncertainty propagates into every inference about orbital radii, in spiral timescales, and gravitational wave frequencies. We are drawing detailed conclusions about a region 20 million kilometers across from an object whose mass we know to within a factor of 2. That black hole is at least an object we can point at. The last 3 items on this list are properties of the universe itself, and the first of them concerns whether empty space is empty. Number 3. The possibility that space itself twists light. The last three items on this list are not objects. They are properties the universe may or may not have, and this is the first of them. The claim is that empty space is not neutral. That a field nobody has identified fills the universe, that it couples to light, and that it has been very slowly rotating the polarization of every photon passing through it for 13.8 billion years. If that is true, it is new physics. Not a new object, not a new class of galaxy, a term missing from the equations that describe how light and matter interact, which have otherwise been the most precisely tested equations in the history of science. The measurement currently sits at somewhere between 2 and 4 sigma, depending on which dataset you use. And there is a paper from January of this year suggesting that everybody may have been measuring the wrong quantity. Start with the idea, which is nearly 40 years old. In 1990, Sean Carroll, George Field, and Roman Jacque worked out what happens if you add a particular term to electrodynamics, a coupling between a hypothetical field and the electromagnetic field, of a form borrowed from a well-studied piece of mathematics. The consequence is specific and testable. Light can be described as a combination of right-handed and left-handed circular polarization, and in ordinary empty space, those two components travel identically. Add the coupling and they travel slightly differently. When you recombine them, the plane of polarization has rotated. Two features make this distinctive. The rotation depends on how much the field has changed over the light's journey, not on how much matter the light passed through. And it does not depend on wavelength. That last property is the crucial one, because there is a well-known effect that does rotate polarization, Faraday rotation, produced by magnetic fields in ionized gas, and Faraday rotation scales with the square of the wavelength. Measure the same rotation at every frequency, and you have ruled it out. It is worth saying that the mathematics involved is not exotic in origin. The term added to the equations is a well-studied structure that appears in topological field theory and in the physics of certain condensed matter systems, where its consequences have been worked out in detail and in some cases observed in the laboratory. Nobody had to invent new mathematics to propose this. The question is only whether nature has chosen to use that particular term at cosmological scales, and if so, what field is attached to it. The place to look is the cosmic microwave background, for three reasons. It is polarized, at about the 10% level, produced by scattering off free electrons 380,000 years after the Big Bang. It is the oldest light in existence, and it has crossed the entire observable universe to get here, which gives any tiny effect the maximum possible distance to accumulate. The polarization pattern across the sky is decomposed into two components with an unlovely pair of names. E modes are gradient-like patterns, radial or tangential around a point. B modes are curl-like, with a handedness to them. The distinction matters because of how they behave under reflection. Hold the sky up to a mirror, and the E modes look the same, while the B modes flip sign, which leads to a clean prediction. In a universe that respects parity, where physics does not distinguish left from right, the correlation between E modes and B modes must be zero. Measure a non-zero correlation, and you have measured a violation of one of the fundamental symmetries of physics in the electromagnetic sector, where it has never been seen. For years, the measurement was blocked by an entirely mundane obstacle. To determine how much the sky's polarization has rotated, you must know precisely how your own detectors are oriented. And no microwave telescope has an absolute polarization calibration on the sky better than about a degree. There is no object of known polarization angle to point at. The effect being sought is a fraction of a degree. The instrument's own uncertainty swamps it, and the two effects are mathematically indistinguishable. A rotation of the sky and a misalignment of the detector produce identical data. It is worth appreciating how ordinary and how intractable that problem is. On the ground, you can calibrate a polarimeter against a wire grid in the laboratory to a fraction of a degree, but the instrument then has to be assembled, mounted, cooled to a fraction of a degree above absolute zero, and pointed at the sky, and every one of those steps can introduce a small rotation. For a satellite, you cannot check afterwards at all. What you would want is a bright astronomical source whose polarization angle is known independently to better than 1/10 of a degree, and there simply is not one. Crab Nebula measurements have been used, and they are good to about 1/2 a degree, which is several times too coarse. For 30 years, the entire field had a systematic uncertainty larger than the effect anybody wanted to measure. Yuto Minami and Eiichiro Komatsu found a way around it in 2020, and the trick is elegant enough to be worth spelling out. Use the Milky Way as the calibrator. Polarized dust and synchrotron emission from our own galaxy is local, a few hundred to a few thousand light-years away. It has not crossed the universe, so it experiences the instrument's misalignment, but essentially none of the cosmological rotation. The microwave background experiences both. That gives you two signals in the same dataset, one carrying one angle and one carrying the sum of two, and if you fit them simultaneously, the angles separate. Applying this to Planck's 2018 polarization data, they measured a rotation of 0.35 degrees with an uncertainty of 0.14. That is a 2.4 sigma exclusion of 0. Suggestive, not conclusive. The follow-ups strengthened it. A 2022 analysis of the reprocessed Planck maps gave 0.30 degrees. Johannes Eskilt and Komatsu combined Planck with WMAP across frequencies from 23 to 353 GHz and obtained 0.342 degrees, excluding 0 at 99.987% confidence, which is 3.6 sigma. And they found no frequency dependence across that entire range, which is what genuine birefringence should look like and what Faraday rotation should not. The caveats are substantial, and the people making the measurement are the ones raising them, which is a good sign. The 2022 Planck analysis found that the measured angle decreases as you mask off more of the galactic plane. That is the signature of contamination. If part of your signal comes from the foreground you are using as a calibrator, removing more foreground should change the answer, and it does. Those authors deliberately declined to claim cosmological significance, pending a better understanding of galactic dust. Dust filaments in the Milky Way do produce their own correlation between E and B modes. It is not zero, and it is not well modeled. Atacama Cosmology Telescope data, released in 2025, gives 0.215 degrees at 2.9 sigma, statistically consistent with Planck, but noticeably lower. A model-independent analysis in October 2025, fitting the total rotation angle across 3 experiments, reached about 7 sigma for the combination. In the same paper, the authors flagged something awkward. The angles inferred independently from Planck and from ACT differ by more than 3 sigma from each other. Their own comment was that this hints an instrumental miscalibration may be preferred over new physics, which is where a paper published in January of this year reframed the entire question in a way that is either a technicality or the most interesting thing about the whole subject. Fumihiro Naokawa, Toshiya Namikawa, Kai Murai, Ippei Obata, and Kohei Kamada pointed out something that had been sitting in plain sight. We only ever observe the polarization as it arrives. A rotation of 0.3 degrees, a rotation of 180.3 degrees, and a rotation of 360.3 degrees all produce exactly the same observed polarization, because polarization is defined modulo a half turn. Naokawa's analogy is that you cannot tell what day it is by looking at a clock face. Their conclusion is that the true rotation angle may be considerably larger than the fraction of a degree being measured, potentially far larger. They also showed that the detailed shape of the EB spectrum encodes the number of half-turns, so the ambiguity is breakable with good enough data. And they showed something unexpected. Once the ambiguity is properly accounted for, birefringence also affects the E-mode spectrum on its own, which may require revising published measurements of the universe's optical depth, and with it, the timeline of reionization. A companion paper proposed an entirely independent test, using the polarization of radio galaxies powered by supermassive black holes. Because the intrinsic polarization angle of a jet is tied to the jet's own geometry, which can be imaged, those objects provide a reference angle that does not depend on any telescope's internal calibration at all. It is worth noticing what kind of measurement this is, because it is characteristic of where physics has ended up. At the start of this list, there was a glow on Venus that 4 centuries of observers have reported and no camera has ever caught, and the absence of an image was the main reason for doubting it. Here, at number 3, the absence of an image is not a problem at all. Nobody expects to photograph cosmic birefringence. There is nothing to photograph. The measurement is a statistical correlation between 2 decomposed components of a polarization field averaged across the whole sky, and if it is real, it will be established by that correlation and by nothing else. The most consequential things we currently measure are not things anybody can look at. So what would it mean if it is real? A field filling space that couples to electromagnetism is not part of the standard model of particle physics. The leading candidates are axion-like particles, which appear in many extensions of the standard model and are also a serious dark matter candidate, ultralight axion dark matter specifically, and, most interestingly, given where this list is going, a slowly rolling quintessence field, which is the leading alternative to a cosmological constant as an explanation for dark energy. That last possibility is worth holding on to. If the rotation is cosmological, then the same field that is driving the accelerating expansion of the universe may also be twisting the polarization of light, and we would have detected it, not through its gravity, but through its effect on photons. 2 of the largest open questions in physics would turn out to be the same question. It would also be a direct violation of parity in the electromagnetic sector. Parity violation is not unprecedented. The weak nuclear force violates it, established experimentally in 1956, but electromagnetism has never shown any sign of it in any laboratory on Earth. It has been connected in the literature to the imbalance between matter and antimatter and to the Hubble tension, because some models that ease the tension generate exactly this coupling as a side effect. There is also a way to distinguish between the candidates, if the effect is confirmed. A field that has rolled slowly and steadily over cosmic time produces a constant rotation angle. A field that is oscillating, which ultralight axion dark matter would do, on a period set by its mass, produces a rotation that varies with time, which means the measured angle would depend on when in the light's journey the rotation happened, and would leave a distinguishable imprint on the shape of the polarization spectrum. Experiments with enough sensitivity and enough sky coverage could separate a rolling field from an oscillating one, and that would be a direct measurement of the mass of a particle nobody has ever detected. The question will be settled, and reasonably soon. Forecasts for Lightbird, a Japanese-led satellite designed for precisely this class of measurement, project that a rotation of 0.3 degrees would be detected at between 5 and 13 sigma, even including foreground contamination and calibration systematics. The Simons Observatory in Chile should push the uncertainty on isotropic rotation from about 30 arc-minutes today down to roughly 1.5. Lightbird should reach about 0.6 of an arc-minute. Within a decade, we will know whether the vacuum has been quietly rotating light since the universe became transparent, or whether several independent teams have spent 15 years measuring the orientation of their own instruments, If the vacuum can have a property we did not know about, the next question is whether the universe can have a direction, and there, the evidence is considerably harder to dismiss. Number 2. The direction the universe should not have. The whole of modern cosmology rests on an assumption so basic that it is usually stated once, in a single sentence, near the beginning of a textbook, and then never mentioned again. On large enough scales, the universe is the same everywhere and looks the same in every direction. It is called the cosmological principle. It is not a minor modeling convenience. It is what makes the equations of general relativity solvable for an entire universe. Einstein's field equations describe how matter and energy curve spacetime, and in full generality, they are far too complicated to solve for something as complex as a universe full of galaxies. What made cosmology a quantitative science was the realization that if you assume the universe is homogeneous and isotropic, the equations collapse into something tractable. Two ordinary differential equations describing how a single scale factor changes with time. Every distance you have ever heard quoted for a galaxy, every age of the universe, every measurement of dark matter or dark energy is derived within that framework. Without the assumption, there is no standard model of cosmology, not because the model would be wrong in some detail, but because the mathematics it is written in would not apply. There is a clean test of that assumption, and the universe is currently failing it by a factor of somewhere between 2 and nearly 4. Start with what is certain. The cosmic microwave background is uniform across the sky to about 1 part in 100,000, with a single large exception. There is a dipole, 1 part in 1,000, one half of the sky slightly hotter than the other, in a smooth gradient between them. This has been understood since it was first measured, and it is not controversial. It is our own motion. We are moving toward the hot side, which blue shifts the radiation coming from that direction and red shifts what is behind us. Planck measures the solar system's barycenter, moving at 369.8 kilometers per second, toward a direction in the constellations Crater and Leo, with an uncertainty of about 1/10 of a kilometer per second. The local group of galaxies as a whole moves at 620 kilometers per second. That is the best measured velocity in astronomy, and it was the first indication that the microwave background could serve as a universal reference frame at all, the closest thing the universe has to a rest frame established from an aircraft in the 1970s before any satellite flew. It is worth asking briefly where that velocity comes from, because the answer is itself not fully settled. We orbit the center of the Milky Way. The Milky Way falls toward the Andromeda Galaxy and the rest of the local group. The local group falls toward the Virgo cluster, and the whole assembly falls toward a much larger concentration of mass in the direction of Centaurus, historically called the Great Attractor, and now understood to be part of the larger Shapley supercluster region. Adding up the gravitational pull of the mass we can actually see in that direction does not obviously account for the full 620 kilometers per second. That has been an open bookkeeping problem for decades, and it is a separate one from what follows. Now the test. In 1984, George Ellis and John Baldwin pointed out that this motion must produce a second, entirely independent signature, and that measuring it would be a direct check of the cosmological principle. If you are moving through a universe filled with distant sources, two effects combine. Doppler boosting makes the sources ahead of you appear brighter, which pushes more of them above whatever detection threshold your survey uses, so you count more of them. And relativistic aberration crowds their apparent positions slightly toward your direction of travel. Both effects work the same way, and both increase the number of sources you count on the side you are moving toward. So the number counts of distant objects across the sky must show a dipole too. And here is the important part. Its amplitude is not a free parameter. It follows analytically from two properties you measure in the same catalog: the slope of the source counts near the flux limit, and the average spectral index of the sources. Feed in the velocity from the microwave background, and the prediction is fixed. It is about as clean a falsification test as cosmology possesses. If the universe is isotropic, and our motion is what the microwave background says it is, the two dipoles must agree. It simply requires an all-sky, uniformly calibrated catalogue of millions of genuinely distant objects, which is why nobody could run it properly until about 5 years ago. In 2021, Nathan Sicrest, Sebastian von Hausegger, Mohamed Ramiz, Roya Mohayi, Subir Sarkar, and Jacques Collin assembled a catalogue of 1.36 million quasars selected in the mid-infrared and ran it. The number count dipole came out more than twice the amplitude the microwave background predicts. The probability of that arising by chance under the standard assumptions was 5 in 10 million, 4.9 sigma. Quasars are the right tool for this, incidentally, because they are extraordinarily luminous, an actively feeding supermassive black hole outshining its entire host galaxy, which means a sample of them is genuinely distant, and local structure cannot dominate it. Their follow-up in 2022 added radio galaxies and did the first joint analysis, matching the two catalogues carefully so that they contained no objects in common and were systematically independent of each other. Different telescopes, different wavelengths, different selection effects. Radio galaxies rejected the null hypothesis at 2.6 sigma on their own, quasars at 4.4. The amplitudes came out at roughly 3 times and roughly 2 times the kinematic expectation. Jointly, 5.1 sigma. An independent Bayesian reanalysis of the same quasar catalogue by Lawrence Dam, Geraint Lewis, and Brendan Brewer in 2023, different statistical machinery, same data, found a dipole 2.7 times the expectation at 5.7 sigma. And in 2025, a result arrived from an entirely different direction. Lucas Boehmer, Dominic Schwarz, Prabhakar Tiwari, and collaborators at Bielefeld combined LOFAR, a low-frequency radio array spread across northern Europe, with 2 further radio surveys. They also introduced a statistical treatment, accounting for something that had been handled crudely before. A single radio galaxy with 2 lobes can be catalogued as multiple separate sources, which inflates counts unevenly across the sky. Correcting for it increases the error bars and makes the result more conservative. Even so, they measure a dipole 3.7 times the standard prediction, at over 5 sigma. Schwarz's own summary of the situation is worth repeating, because of how carefully he framed the choice. If our solar system is indeed moving this fast, he said, we need to question fundamental assumptions about the large-scale structure of the universe. Alternatively, the distribution of radio galaxies itself may be less uniform than we have believed. Those are the 2 doors, and neither is comfortable. There are 3 ways out on the table. The first is that the anisotropy is real, that the universe genuinely is not the same in every direction on the scales being probed, which means abandoning not merely the standard cosmological model, but the metric it is written in. Tilted universe models and anisotropic expansion models are being explored, and they are not small modifications. They change what a redshift means. That last point deserves unpacking, because it is why the stakes here are higher than the sigma count suggests. In the standard framework, a galaxy's redshift is converted into a distance by assuming the universe expands at the same rate in all directions, so that redshift depends only on how long the light has been traveling. If expansion is even slightly anisotropic, that conversion becomes direction dependent. Every distance in every catalogue would acquire a correction that depends on where in the sky the object sits. And since dark energy was discovered by comparing the brightness of supernovae against their redshift-derived distances, a direction-dependent error in that conversion propagates directly into the thing this list ends on. The measurements would not become worthless. They would become measurements of something slightly different from what everybody has assumed they were measuring. The second is an intrinsic clustering dipole. Structure in the relatively nearby universe, leaking into a sample that was supposed to be purely distant, producing an excess that has nothing to do with motion. The third is catalog systematics, flux calibration that drifts across the sky. And specifically, the fact that the survey satellite's scanning pattern imprints depth variations aligned with the ecliptic plane, which is uncomfortably close to some of the directions involved. The counter-analyses are serious and should be taken seriously. A 2024 paper argued that the systematic uncertainty is being badly underestimated. The quasar distribution they showed carries low-order multipole patterns of comparable amplitude to the dipole itself, patterns that are unexpected and presumably systematic in origin. And the galactic sky cut, which removes roughly half the sky where our own galaxy blocks the view, couples multipoles together. The mask's own quadrupole mixes the dipole with the octopole, which inflates the true uncertainty on the dipole beyond what a naive calculation gives. A November 2025 analysis built detailed simulations including quasar clustering bias, the radial selection function, and the exact sky coverage, and revised the significance down to somewhere between 3.3 and 3.6 sigma. That is a substantial reduction. But their own conclusion was explicit. The anomaly is reduced, and it cannot be explained solely by the clustering dipole or by mode coupling from the survey mask. And there is a straightforward contradiction sitting in the literature. A 2022 study, using 2 different radio surveys, reported that radio galaxy counts and fluxes are consistent with the microwave background dipole, full stop. So independent analyses of overlapping data land anywhere from 3.3 sigma to 5.7, and different radio catalogs disagree with each other. That is what an unresolved measurement looks like. The field now has a formal review in Reviews of Modern Physics, published in 2025 by the group that has pushed this hardest. SARCA's public summary this month is that the universe fails the Ellis-Baldwin test, and that the community has largely ignored it, not out of carelessness, but because there is no easy patch. You cannot add a parameter and move on. Fixing it means discarding the metric and starting over, and almost nobody wants to be the person who starts that. There is something worth saying about that reluctance, because it is easy to hear as an accusation of intellectual cowardice, and it is not quite that. Every working cosmologist has a set of tools that function. Distances get computed, surveys get planned, papers get written, and the framework delivers answers that agree with each other across a remarkable range of independent measurements. A 4 sigma anomaly in one test is not, on its own, enough to abandon a framework that works. The history of physics is full of anomalies at that level that turned out to be systematics. The problem is specific to this case. Because there is no partial repair, there is also no cheap way to take the anomaly seriously. You either continue as before or you rebuild. That is an unusually unpleasant choice, and it is why the number count dipole has been discussed far less than its statistical significance would suggest. The instruments that will settle it are arriving. The Rubin Observatory in Chile, which will image the entire southern sky every few nights for a decade and will catalog objects in numbers that make current quasar samples look preliminary. DESI's quasar samples, already in hand. Euclid, which is surveying a third of the sky from the second Lagrange point. SPIREX, which maps the whole sky spectroscopically. And the Square Kilometre Array, whose radio source counts will eventually run to tens of millions across both hemispheres, with calibration designed from the outset with tests like this in mind. None has yet published a decisive dipole measurement, and all of them will be able to. The excess is in amplitude, not direction, and that is what makes a pure systematic hard to argue for. The number count dipole points roughly where the microwave background dipole points. A calibration error across the sky has no particular reason to align itself with the direction of our motion through the galaxy. Something is producing a dipole in the right place and the wrong size. This does not sit alone, though the other cases are weaker and should be presented as such. The microwave background has its own set of large-angle oddities. There is the alignment of the quadrupole and the octupole, the two largest scale patterns after the dipole, with each other, and roughly with the plane of Earth's orbit, which is a plane that should have no cosmological significance whatsoever. That was first flagged in the WMAP data, and it persisted in Planck. There is also a hemispherical power asymmetry, with more small-scale structure in one half of the sky than the other. Planck's own analyses stress the limits here, and the limit is fundamental. At the largest angular scales, there are only a handful of independent patterns on the sky to measure, so the statistical uncertainty is irreducible. There is only one sky. No better instrument will ever make those anomalies more significant, because the limitation is not the instrument. What makes the number count dipole different is precisely that it is not a statistical fluke argument. It is not a claim that a pattern looks surprising. It is a direct comparison between two measurements of the same physical quantity, our velocity, using two completely independent methods that must agree if the framework holds. They do not agree, and nobody has produced a repair that leaves the foundations intact. Which leaves one item, and it is the only one on this list that is not about something we never knew. It is about something we thought we had already settled. Number 1. The evidence that dark energy is not a constant. For 27 years, the ending of the universe was a settled question. In 1998, two competing teams measuring the brightness of distant supernovae found the same unexpected thing. Both had set out to measure how fast the expansion of the universe was slowing down, because everyone assumed gravity must be gradually pulling the brakes on it. Instead, they found that the expansion is speeding up. It won the Nobel Prize in 2011, and it was, in the most literal sense, an accidental discovery. Nobody was looking for it. Whatever is driving that acceleration was named dark energy, which is a placeholder rather than an explanation. And the simplest possible form it could take is a cosmological constant, an energy density belonging to space itself, the same in every cubic meter, unchanging, identical now to what it was 10 billion years ago and what it will be 10 billion years hence. If that is what it is, then the future is not in question. Space keeps expanding, and because the energy density of space does not dilute as space grows, the acceleration continues without limit. Every galaxy outside our own local group eventually recedes faster than light can cross the gap and disappears over the horizon. Star formation ends when the gas runs out. The last stars burn down. The universe becomes dark, dilute, cold, and stays that way permanently. It is worth saying how much of the universe this concerns. Dark energy accounts for roughly 68% of the total energy content of the universe. Dark matter accounts for about 27%. Everything made of atoms, every star, every planet, every telescope, every person who has ever wondered about any of this, comes to about 5%. The question of what dark energy is, and whether it changes, is a question about 2/3 of everything. And the cosmological constant has never been comfortable, even when it fitted every measurement. Quantum field theory says empty space should have an energy density of its own, arising from the fluctuations of the fields that fill it. Calculate what that density ought to be, and compare it with the value we actually measure, and the two differ by something like 120 orders of magnitude. That is not a rounding error or a factor anybody has overlooked. It is routinely described as the worst quantitative prediction in the history of physics, and it has been sitting there, unresolved, for the entire period during which the cosmological constant was the accepted answer. That has been the standard answer since the turn of the century. Since 2024, the evidence has been drifting away from it, and the honest position in 2026 is that we no longer know how this ends. The instrument doing the drifting is called DESI, the Dark Energy Spectroscopic Instrument, and it is mounted on a 4-meter telescope that has been on Kitt Peak in Arizona since 1973. Its defining piece of hardware is an array of 5,000 robotic fiber positioners packed into the telescope's focal plane. Each one holds an optical fiber and can move it to a precise position so that 5,000 objects can be observed at once, and the whole plane can be reconfigured between exposures. More than 900 researchers from over 70 institutions work on it. Picture it running. The dome is open, the desert is cold, and between one exposure and the next, 5,000 small mechanisms move at once, a sound somewhere between rainfall and a swarm, each one placing a fiber on a target selected years in advance from an earlier survey. Then the shutter opens, and for 20 minutes those fibers collect photons that in many cases left their source before the sun existed. The whole array is doing one thing, measuring the redshift of every one of those objects precisely enough to place it in a 3-dimensional map. And out of that map comes the number that decides whether the universe ends cold or ends closed. The measurement rests on the oldest ruler in existence, and it is worth understanding because it is genuinely beautiful. Before the universe cooled enough for atoms to form, it was a plasma of photons and charged particles tightly coupled together. In that state, pressure waves could propagate, actual sound, in a medium with the density of the early universe. Every region that was slightly denser than average launched a spherical sound wave outward. When the universe cooled and the photons decoupled, the pressure vanished, and those waves froze wherever they had got to. That left a preferred separation between matter concentrations, a faint ring of enhanced density at a fixed radius around every original overdensity. It is called the Baryon Acoustic Oscillation Scale. It is about 500 million light-years across, and it is imprinted in the distribution of galaxies to this day. The point of a standard ruler is that you know its true size. And this one's true size can be calculated from first principles, from the temperature of the microwave background and the density of ordinary matter, both measured independently. So you measure how large it appears in galaxy surveys at different redshifts, compare with how large it should be, and you have measured the expansion history of the universe directly, without any of the calibration chains that make supernova distances contentious. DESI's first cosmology results came out in April 2024, giving near% distance precision across 7 redshift bins. When they fitted a model in which dark energy is allowed to vary, where its equation of state is described by a present value plus a term allowing it to evolve, the data preferred a present value greater than -1 and an evolution term less than 0. A cosmological constant requires the equation of state to be exactly -1, forever. What the data preferred was dark energy that was stronger in the past and is weakening now. The second release came in March 2025, using nearly 15 million galaxies and quasars, more than double the first, tracing the influence of dark energy across 11 billion years of cosmic history. The analysis was blinded, the results hidden from the people performing the analysis until the method was frozen, which is now standard practice in cosmology precisely because the field has been burned before by unconscious tuning toward the expected answer. DESI's acoustic measurements on their own remain consistent with a cosmological constant. That should be stated plainly. It is when they are combined with the microwave background, with supernovae, and with weak gravitational lensing that the preference for evolving dark energy appears, 2.8 sigma using one supernova compilation, 3.8 using a second, and 4.2 using a third. A representative fit gives a present-day equation of state of -0.838, where a constant requires exactly -1. That spread is the heart of the argument against it, and it is a fair argument. 2.8 to 4.2 sigma from identical acoustic and microwave data, depending only on which supernova catalog you attach to it. That is not what a robust result usually looks like. George F. Stathiou made the sharpest version of the objection. He compared the roughly 20% of supernovae that appear in two of the compilations and found an offset of about 0.04 of a magnitude between low redshift and high redshift distances. Subtract that offset across the whole sample, and the preference for evolving dark energy deflates substantially. The rebuttal, published in 2025, attributes most of the offset to different treatments of selection bias, 43% to genuine improvements in the newer sample's modeling of intrinsic scatter and host galaxy properties, and 38% to the fact that comparing objects one by one across surveys with different selection functions is misleading in the first place. Even forcing the older, less sophisticated model, they find the evidence drops only from 3.9 sigma to 3.3. A different criticism cuts another way. Marina Cortez and Andrew Liddell argue that the whole exclusion is really a detection of one parameter inside one specific mathematical form for how dark energy might evolve, and that the most secure inference is the 3.1 sigma exclusion from the acoustic and microwave data alone, dropping supernovae entirely. And there is a theoretical difficulty that nobody has resolved. The best-fitting region has the equation of state crossing -1 at some point in cosmic history. A single rolling scalar field, the simplest and most studied alternative to a cosmological constant, cannot do that. Whatever this is, if it is real, it is not the simplest version of the simplest alternative. The theoretical response has been to construct models in which two components, or a field with unusual properties, allow the crossing to happen. And a small industry of such papers has appeared since 2025, which is itself a reasonable indicator of how seriously the observational result is being taken. DESI completed its originally planned 5-year survey on the 15th of April this year, having observed more than 47 million galaxies and quasars against a target of 34 million, plus over 20 million stars, and it is continuing to extend its coverage. A 2026 analysis reports independent evidence of evolving dark energy from the Lyman alpha forest, the dense picket fence of absorption lines that intervening hydrogen clouds imprint on the spectrum of a distant quasar, turning a single object into a core sample of everything between it and us. Euclid is surveying. The Rubin Observatory is beginning the deepest supernova survey ever attempted. The Roman Space Telescope is coming. Between them, this will be settled. There is one further result that is worth stating because it runs opposite to what people expect. Fitting an evolving dark energy model to the DESI data yields a Hubble constant lower than the value derived from the microwave background, which means that evolving dark energy does not resolve the long-running disagreement over the expansion rate. It makes it worse. And that brings this list to the place it has been heading all along. There is a phrase worth remembering from earlier in this countdown. Before 2005, the standard solar model matched helioseismic measurements to better than 0.5%, and that agreement was held up as proof that we understood the inside of a star. Then a better measurement broke it, and it has stayed broken for 21 years. The cosmological constant has been in exactly that position. For 27 years it fitted everything: supernovae, the microwave background, galaxy clustering, gravitational lensing. It is the sixth number in a 6-parameter model that explains the entire universe, and by any reasonable standard it worked. The pattern this list keeps finding is that the tightest agreements are the ones with the furthest to fall, and that a model matching beautifully is not the same as a model being right. That is why this is number 1, rather than anywhere else. Every other entry on this countdown is about something we cannot currently explain. A glow on Venus. 2 lunar hemispheres that do not match. A supernova nobody in Europe recorded. 5 men and a flame on the moon's horn. A disk of bronze and a tablet of clay. A sun too dim for the world it warmed, and a sun we cannot simulate. Galaxies that assembled too fast. A signal under an Italian mountain. A black hole that lost its corona. A possible twist in the vacuum. A direction the universe should not have. All of those are gaps in what we know. This one is different. This is something we thought we had already closed. If dark energy is a constant, the far future is a known quantity, and it is slow and cold and permanent. If its density is falling, then acceleration is a phase rather than a destiny. The expansion could slow. It could stop. In models where the dark energy density crosses 0 and turns negative, it reverses, and everything that has been flying apart for 13.8 billion years comes back together. The observational difference between those two futures is a few hundredths in a single parameter, measured today from 15 million galaxies. This list has kept running into that. 2% of solar luminosity is the difference between a habitable Earth and a frozen one. A fraction of a degree of polarization rotation is the difference between an empty vacuum and one filled with an unknown field. A factor of 2 in a dipole amplitude is the difference between a universe with no preferred direction and one that has one. The decisive quantities in this subject are almost always small, and smallness has never had anything to do with importance. We do not know which universe we are in. Not because nobody has looked, and not because the question is beyond us, but because the measurement is genuinely close, and the instruments that will decide it are still gathering light. That is the honest state of it in 2026, and it is a strange thing to sit with, not frightening exactly, but unfamiliar. A conclusion you had already absorbed, filed away, stopped thinking about, has quietly become provisional again. And there is something worth taking from that at the end of 4 hours of open questions. Every item on this list is unresolved because somebody kept measuring after the answer looked settled. That is the whole method. It is slow, it is unglamorous, and it is why a glow on Venus is still an open file after 383 years, and why the ending of the universe is once again something we are allowed to wonder about. None of it needs to be settled tonight. Sleep well, and good night.